Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're going to begin with one of the quietest and strangest questions a human mind can ask. How did the first atom come from nothing? It is the sort of question that sounds simple at first, almost like something a child might ask while looking up at the night sky from the backseat of a car. But the longer you sit with it, the deeper it becomes, because an atom is not just a tiny speck of matter. It is the beginning of chemistry. It is the start of stars, planets, oceans, dust, air, skin, bread, tea, and the small crumbs that somehow appear in the corner of a kitchen, no matter how often anyone cleans it. Atoms are the alphabet of ordinary things, and yet there was a time when even atoms did not exist. No hydrogen, no helium, no carbon, no oxygen, no little building blocks waiting patiently in a cosmic storage cupboard. The universe had to make them, and before it could make them, it had to become the kind of place where matter could survive at all. So tonight, as you settle in, I would love to ask you something gentle before we begin. Where are you listening from right now? Are you somewhere dark and quiet, with the room already soft around the edges? Are you in bed, on a sofa, in a chair, perhaps telling yourself that you will only listen for a few minutes, and then somehow finding that the universe has other plans? And if you can, take a moment to notice the objects around you. Maybe a blanket, a pillow, a glass of water, a wall, a window, your own hands resting nearby. Every one of those things is made of atoms. And those atoms have a history far older than any country, any language, any mountain, or any ocean. They come from a story that began when the universe was so hot, so dense, and so unfamiliar that the word thing barely applied to anything yet. If you find this quiet journey soothing, or if it gives your mind a calm place to wander at the end of the day, I would be ever so grateful if you gave the video a like and perhaps subscribed. It helps this little corner of science and sleep reach others who may also enjoy drifting through the universe one gentle idea at a time. And I do hope this question is not so interesting that it keeps you wide awake. But if it does, well, at least you will be awake in good company, somewhere near the beginning of everything, waiting for the first atom to arrive. Now, before we go any further, we should be careful with the word nothing. In everyday life, nothing usually means an empty room, an empty cup, or the place in the fridge where you were quite sure there was still a slice of cake. But in physics, nothing is a much slipperier word. Empty space is not truly nothing. A vacuum is not truly nothing. Even darkness is not nothing, because darkness is still space where light is absent. When we talk about the universe beginning from nothing, we are stepping into a region where language begins to creak a little under the weight of the idea. We're not simply imagining a large empty box before the universe appeared, because a box would already be something. It would have space inside it. It would have boundaries. It would have time in which nothing was happening. But if space and time themselves are part of the universe, then asking what happened before, the universe may be a bit like asking what is north of the North Pole. It sounds like a normal question, but the usual map no longer works. That does not mean the question is meaningless. It means we have to approach it slowly. We have to let our minds become comfortable with the possibility that the beginning was not a scene, not a place, and not a moment in the ordinary sense. There may not have been an empty stage waiting for the universe to walk on. The stage itself may have come into existence with the performance. Space, time, matter, energy, and all the rules that tell them how to behave may have begun together, not as separate ingredients poured into a bowl, but as one unfolding event. Which is slightly inconvenient if you are hoping the universe came with clear instructions, a tidy label, and perhaps a small diagram on the side. The first atom did not appear instantly. It was not the first thing the universe made. In fact, atoms are rather delicate compared with the conditions at the beginning. We think of atoms as tiny and sturdy, and in everyday life they certainly behave that way. The atoms in a stone can sit there for ages, looking very committed to the idea of being a stone. But in the earliest universe, the conditions were far too violent for atoms to hold together. The universe was not yet a calm place where electrons could settle around nuclei. It was more like an unimaginably hot ocean of energy and particles, too crowded and too restless for structure. If an atom had tried to form too early, it would have been torn apart almost immediately, rather like trying to build a snowman inside a furnace. A noble effort, perhaps, but not one with a long future. So the story of the first atom is not only the story of matter appearing, it is also the story of waiting. The universe had to expand, it had to cool, it had to pass through stages where different kinds of particles became possible, then stable, then able to combine. Each step depended on the universe becoming slightly less extreme than it had been before. Not quiet, exactly, not for a very long time, but less overwhelmingly hot, less dense, more capable of allowing small arrangements to persist. The first atom was not a sudden magic trick. It was the result of a long chain of changes, each one making the next one possible. At the beginning of this journey, there were no atoms because there were no atomic pieces in the familiar sense. There were no little solar systems with electrons circling like planets, although that picture itself is a little misleading, and we will treat it gently when the time comes. There were no protons quietly waiting to become hydrogen. There were no neutrons packed into nuclei. There were not even, for the earliest moments we can describe, particles behaving in the calm and separate way we're used to imagining them. The universe was so hot that energy itself could produce particles, and particles could vanish back into energy. Creation and destruction were not rare events, they were the normal weather. This is where the phrase "from nothing" becomes more subtle. Physics does not describe the early universe as something appearing in the same way a rabbit appears from a magician's hat. For one thing, a magician's hat is already suspiciously full of possibilities, and usually belongs to someone who has practiced the trick rather more than they admit. Instead, modern cosmology suggests that the early universe was a state where energy, space, time, and quantum uncertainty were deeply connected. In quantum physics, empty space is not a dead emptiness. It has activity. It has fluctuations. It has the possibility of change built into it. But again, we must be cautious, because when we talk about quantum fields or vacuum states, we are already talking about a physical framework. That is not absolute nothing in the philosophical sense. It is not a blank beyond all existence. It is physics describing the simplest kinds of physical reality we know how to talk about. And perhaps that is part of the wonder. Science may not be able to point to absolute nothing and say, "There, that is where the atom came from," as if nothing were a field on a map. What science can do is follow the evidence backward. We can look at galaxies racing away from each other. We can observe the faint afterglow of the early universe stretched into microwave light. We can measure the amounts of hydrogen and helium scattered across the cosmos and compare them with what our models predict. Again and again, the evidence tells us that the universe was once hotter, denser, and simpler. It tells us that atoms formed only after a period when matter was too energetic to become ordinary matter. It tells us that what now seems solid and familiar began in conditions so extreme that familiarity itself had not yet been invented. Imagine, very gently, turning the clock of the universe backward. Not your bedside clock, of course. That one may already be judging you for how late it is. Imagine instead rewinding the expansion of space. Galaxies draw closer together. The spaces between them shrink. The universe becomes hotter. Starlight disappears into a denser glow. Planets are undone. Stars are unmade. Atoms are pulled apart. Nuclei are broken. Protons and neutrons lose their identities. The universe becomes less like a collection of objects and more like a blazing, crowded state of raw physical possibility. Keep going, and even our best theories begin to struggle. We can describe much of what happened after the earliest instant, but the very beginning remains one of the deepest frontiers in science. That is not failure. It is the honest edge of knowledge. Physics is very good at explaining how the universe changed once certain conditions existed. It can tell us how particles formed, how nuclei formed, and how atoms eventually became possible. It can tell us why hydrogen was the first and simplest atom to emerge in abundance. It can explain why the early universe glowed, why it became transparent, and why that ancient light still fills the sky today. But the question of why there is something rather than nothing reaches beyond the normal comfort of laboratory reasoning. It touches cosmology, quantum theory, philosophy, and perhaps the limits of what a universe can know about its own beginning, which is quite a lot to place on a sleepy evening, so we will take it one calm step at a time. The first atom, when it finally arrived, was most likely hydrogen in the simplest sense. A single proton holding onto a single electron. That sounds modest, almost too modest. After all the grandeur of the beginning, after heat beyond imagination, after space expanding and energy transforming, the first familiar atom was not a diamond, not gold, not oxygen, not anything dramatic enough to deserve a trumpet. Just hydrogen. The simplest atom, the lightest atom, the quiet first word of chemistry. And yet from that simplicity came nearly everything else. Hydrogen would gather into vast clouds. Gravity would pull those clouds together. Stars would ignite. Inside stars, simple atoms would be pressed and fused into heavier ones. Later, when stars died, they would scatter those atoms outward, seeding the universe with the ingredients for planets, and eventually living things that could lie awake at night wondering where atoms came from. There is something grounding about this. The first atom was not complicated. It did not need to be. The universe often begins its most important work with simple pieces. A proton, an electron, a bond formed when conditions finally allowed it. That is the beginning of ordinary matter as we know it. Not the beginning of all existence, but the beginning of a universe that could become transparent, structured, and eventually chemical. Before atoms, light could not travel freely for long. It was constantly scattered by loose charged particles. The early universe was filled with a glowing fog. Only when electrons finally joined with nuclei did space become clear enough for light to move across the cosmos. The first atoms did not only create matter as we know it, they helped open the universe. But we are getting slightly ahead of ourselves, as the universe often encourages us to do. To understand the first atom, we first need to understand why there was a time before atoms. That means stepping into the earliest conditions we can describe, when the universe was not yet filled with objects, but with energy and fields, with particles forming and vanishing, with forces that may once have been joined together in ways we do not yet fully understand. It means asking how matter can emerge from energy, why matter did not vanish completely with antimatter, and how the tiny ingredients of atomic nuclei came to be. None of this needs to be rushed. In fact, rushing would be rather rude to the universe, which took its time cooling down before giving us anything as comfortable as chemistry. So let us begin softly, not with an atom, but with the absence of atoms. Let us picture, as best we can, a universe so young that the familiar categories of the world had not yet formed. No dust, no gas clouds, no stars, no empty night between stars, no planets turning quietly in space, no molecules drifting through the dark, not even darkness in the way we know it, because darkness needs light to be absent from somewhere, and the early universe was not yet organized into somewhere and elsewhere in the usual sense. What existed was a hot, dense, rapidly expanding state. Every part of the observable universe today was once compressed into conditions beyond ordinary intuition. The distances that now separate galaxy clusters were once part of a much smaller, hotter whole. When people hear this, they sometimes imagine the Big Bang as an explosion in space, like a firework bursting into a pre-existing darkness. But that image is not quite right. It was not matter exploding outward into empty space. It was space itself expanding. The universe did not have a centre where the explosion happened. Every region of space was once closer to every other region. The expansion happened everywhere. If that feels hard to picture, that is perfectly fine. The human brain evolved to understand falling fruit, weather, faces, footsteps, and whether a rustling bush was about to become a problem. It did not evolve to comfortably imagine all of space expanding from a hotter, denser state. So if your mind gently protests, it is not being difficult. It is simply being a mammal. A useful way to think about it is not to ask where the Big Bang happened, but when the universe was hot and dense. Everywhere we can observe was once part of that early state. The first atom did not form at one special point, like a tiny bead appearing in the middle of a room. Atoms formed throughout the universe when the conditions became right. The universe cooled everywhere as it expanded. Nuclei and electrons found each other everywhere. Hydrogen appeared not as a single lonely atom holding up a little flag, but as part of a vast cosmic transition from a charged fog into a transparent universe. Still, the phrase "the first atom" remains useful because it directs our attention to a threshold. Before that threshold, no stable atoms. After it, the universe could begin behaving in a way that leads toward the matter we know, and this threshold depended on temperature. Heat in physics is not just warmth as we feel it on skin. It is the motion and energy of particles. In the early universe, particles were moving with such intense energy that any attempt at stable structure was constantly disrupted. As space expanded, the energy spread out. The universe cooled. This cooling did not happen because the universe was losing heat into some outside room. There was no outside room, no cosmic kitchen counter on which the universe could cool like soup. The expansion of space itself stretched the energy within it. Light was stretched to longer wavelengths. Particles became less energetic, conditions changed. Slowly the universe became less hostile to structure. That word structure is important. An atom is structure, a nucleus is structure, a star is structure, a galaxy is structure. You are structure, though hopefully a relaxed one at this point. The history of the universe is in many ways a history of structure emerging as conditions allow. First, the simplest particles, then composite particles, then nuclei, then atoms, then clouds, then stars, then heavier elements, then planets, then chemistry complex enough for biology. Each stage depends on the stage before it, and each stage becomes possible only when the universe has changed enough for nature to try something new. So when we ask how the first atom came from nothing, we are really asking several questions braided together. How did the universe begin in a state where matter could eventually exist? How did energy give rise to particles? How did some of those particles survive? How did protons and neutrons form? How did nuclei appear? How did electrons finally settle into place? And why did the universe become calm enough for a simple atom to last? The answer is not one single event, but a sequence. Not a snap of cosmic fingers, but a long transformation from extreme simplicity into the first hint of ordinary matter. Tonight we will start at the edge of that transformation, with the universe before atoms, before chemistry, before any familiar object had a name or a shape. We will move slowly through the heat, the cooling, the particle soup, and the patient arrival of structure. We will keep our feet on the ground where we can, and when the ideas become strange, we will let them be strange without forcing them to become ordinary. After all, the universe is under no obligation to make immediate sense to a creature who occasionally forgets why they walked into a room. For now, simply notice this. The atoms around you are not just tiny pieces of matter. They are survivors of a long cosmic process. The hydrogen in water, the carbon in your cells, the oxygen you breathe, the atoms in the blanket near you, all of them belong to a history that began before there were atoms at all. The first atom was not made in a quiet workshop. It emerged from a universe learning how to cool, how to separate, how to hold itself together in small, stable forms. And before we can meet that atom properly, we need to drift back to the time when the universe had no atoms to offer, only heat, expansion, and the first conditions from which matter would eventually begin to take shape. To understand how the first atom could appear, it helps to spend a while in the universe before atoms, which is not a comfortable place to picture. Not uncomfortable in the way a cold room is uncomfortable, or a chair with one slightly shorter leg, though both are serious matters in their own small way. It is uncomfortable because almost every familiar idea we use to describe reality begins to fail. There were no objects in the ordinary sense, no rocks, no dust, no air, no stars, no glowing clouds, no black sky stretched between distant points of light. There was no chemistry, because chemistry needs atoms, and atoms had not yet formed. There was no solid surface on which anything could rest, no empty background into which matter had been scattered, no quiet darkness waiting for a sunrise. The universe was present, but it was not yet the kind of universe that could be furnished. When people imagine the earliest universe, they often imagine a tiny glowing ball sitting somewhere in darkness, waiting to explode. It is a natural picture, because we are used to things happening inside space. Fireworks burst in the sky, a match lights in a room, a kettle boils on a stove. But the beginning of the universe was not an explosion placed inside a larger emptiness. It was not a bright object surrounded by blackness. Space itself was in the hot, dense state. Every region that would one day become part of the observable universe was packed into conditions so extreme that distance, temperature, and energy were far beyond everyday comparison. The universe did not expand into a room. It expanded as the room, the walls, the distances, and the possibility of there being a room at all. That is why the phrase "no shape" is useful, as long as we treat it gently. It does not mean the universe was shaped like a blob or a ball or a cloud with soft edges. It means that the familiar structures we use to orient ourselves did not yet exist. Shape usually requires contrast. A stone has a shape because it has a surface, and beyond that surface is air, water, soil, or perhaps the bottom of someone's shoe if they were not watching where they were going. A star has a shape because there is a difference between the hot glowing plasma inside it and the space outside it. A galaxy has a shape because stars gather in patterns against darker regions. But in the very early universe there were no stars or galaxies, and no surfaces that separated one ordinary object from another. There was no chemistry to make solids or gases as we know them. There was no matter arranged into clear boundaries. There was mostly a dense, hot, uniform state, changing everywhere at once as space expanded. Uniform does not mean perfectly simple, and this detail matters. The early universe was remarkably smooth on large scales, but not perfectly smooth. There were tiny differences in density from place to place. These differences were incredibly small, but later they would become very important. They were the faint beginnings of future structure. One slightly denser region could eventually attract more matter through gravity. Over vast stretches of time, those tiny early irregularities would grow into the first stars and galaxies. In the beginning, however, they were not stars in waiting in any obvious visual sense. They were just small variations in a hot field of particles and radiation. If you had somehow been able to stand there, which you could not, because standing requires ground, atoms, temperature limits, and a body that is not instantly converted into a very brief physics demonstration, you would not have seen little seeds of galaxies floating around. There would have been no ordinary seeing at all. This brings us to the idea of no light, which also needs careful handling. The early universe did contain light in the broad physical sense. It contained radiation, and radiation was everywhere. But it was not light travelling freely across space the way starlight crosses the night sky now. It was trapped in a dense crowd of charged particles. Imagine trying to walk through a room so packed with people that every step sends you bumping into someone. Except now, imagine that you are a particle of light. The room is the entire universe, and everyone is moving with absurd enthusiasm. A particle of light could not travel far before interacting with charged matter. It scattered again and again. The universe was glowing, but it was also opaque. It was bright in the sense of being filled with energy, yet there was no clear view through it. There were no distant objects to see, and no long path for light to take without interruption. This is a strange idea, because we usually think of brightness and visibility as the same thing. If a room is bright, we can see across it. If the sun is shining, we can see the garden, the pavement, the neighbour's cat making serious decisions about a fence. But a glowing fog can be bright and still impossible to see through. The early universe was more like that. It was not dark, but it was not transparent. Light was constantly being absorbed, emitted and scattered. Only much later, when electrons joined with nuclei to form neutral atoms, would light finally travel freely for long distances. That ancient released light is still present today, stretched and cooled by the expansion of space into a faint microwave glow that fills the universe. But before atoms, that freedom had not arrived. Light was not yet a messenger crossing the cosmos. It was part of the restless crowd. No, chemistry may be the easiest part to understand, because chemistry depends on atoms and electrons arranging themselves in stable ways. In our world, chemistry is everywhere. It is in the browning of toast, the scent of rain on warm pavement, the fizz of a drink, the burn of a candle, the way soap loosens oil from skin, and the slightly mysterious transformation of dough into bread, which still feels a little magical even when you know the science. But all of these processes require atoms and molecules. They require electrons to be held around atomic nuclei. They require temperatures low enough for bonds to form and last. In the early universe, none of that was possible. It was too hot, too dense, too energetic. Any delicate arrangement would be torn apart almost as soon as it began. Chemistry needs patience, and the young universe had not yet learned patience. Before chemistry, matter itself had to become stable. In the earlier stages, we can discuss with some confidence, the universe was filled with particles and radiation, in a state often described as a hot plasma. Plasma is sometimes called a fourth state of matter, though that phrase can make it sound like it is waiting politely after solids, liquids, and gases in a school textbook. Plasma is what you get when matter is so energetic that electrons are not bound to nuclei. It is a sea of charged particles. The sun is made mostly of plasma. Lightning is plasma. Neon signs contain plasma, giving us the useful reminder that even strange physics can eventually be used to advertise late-night noodles. The early universe was not exactly like a neon sign, of course. It was vastly hotter and denser. But the comparison helps in one small way. It reminds us that matter does not always come in the calm forms we meet at room temperature. Yet even plasma is a later and more organized description than the very first moments. Before there were atomic nuclei, before there were stable protons and neutrons in the familiar sense, the universe passed through a state where the ingredients of those particles moved freely in an incredibly hot soup. These ingredients are called quarks and gluons. Quarks are among the fundamental pieces that make up protons and neutrons. Gluons help bind quarks together through the strong nuclear force. In today's universe, quarks are almost never found alone. They're confined inside larger particles. But in the extremely early universe, temperatures were so high that quarks and gluons formed a kind of dense fluid, not yet locked into the protons and neutrons that would later become the hearts of atoms. This is one of those places where the universe sounds less like a tidy machine and more like a kitchen, in which every ingredient is flying around before anyone has found the mixing bowl. But it was not chaos without rules. Physics was still operating. Forces were acting. Particles were interacting. The universe was changing according to deep patterns, even if those patterns led to conditions we cannot picture directly. As it expanded and cooled, free quarks became bound together into protons and neutrons. That was a major step toward atoms, but it was still not enough. A proton by itself can become the nucleus of hydrogen, but it cannot become an atom until it captures an electron and keeps it. And for a long time, the universe was too hot for that. The absence of atoms also meant the absence of ordinary materials. There was no gas in the everyday sense, though we often use the word gas loosely when discussing cosmic material. There were no clouds like the clouds above Earth, no vapour drifting quietly through space, no dust grains, no ice crystals, no smoke, no minerals. A mineral is an arrangement of atoms. A dust grain is a collection of atoms. A molecule is atoms joined together. Without atoms, all of these familiar things are impossible. The universe had not yet reached the stage where it could make grains, droplets, surfaces, crystals, or cells. It was physically real, full of energy and activity, but not yet able to make the ordinary textures of existence. It is worth pausing over how different this is from emptiness. The early universe before atoms was not empty. It was intensely full. It was full of energy, radiation, particles, antiparticles, interactions, and rapid change. The nothing in our larger question is not a quiet, empty space filled with boredom. It is a deeper question about why there is a universe at all. Once the universe exists in a hot, dense state, even without atoms, it is already very much something. In fact, it is so much something that it cannot yet form the simple structures we take for granted. Sometimes too much energy prevents structure. A snowflake needs cold, a soap bubble needs surface tension and air, a cake needs heat, but not the heat of the centre of a star, unless the recipe is unusually ambitious and the kitchen has excellent insurance. Atoms needed the universe to calm down. Cooling did not happen because the universe sat in a colder environment. There was no outside refrigerator for the cosmos, no great celestial windowsill where reality could be left to cool overnight. The universe cooled because space expanded. As space stretched, radiation lost energy. Particles interacted differently, conditions changed. Temperature fell. The early universe was still hot by any ordinary standard for a long time, but it became less violently hot. This gradual cooling allowed new forms of stability to appear. First, certain particles could survive. Later, protons and neutrons could combine into simple nuclei. Much later still, electrons could remain bound to nuclei, forming atoms. The order matters. If we try to put atoms too early, we run into a problem. Atoms are held together by electrical attraction between negatively charged electrons and positively charged nuclei. But in the early universe, the particles had so much energy that electrons could not stay attached. They were constantly knocked free. So even after nuclei existed, the universe remained without atoms for a long stretch of time. It had atomic nuclei and electrons, but not neutral atoms. That distinction can seem small, but it changed everything. A universe filled with loose charged particles scatters light and remains opaque. A universe filled mostly with neutral atoms lets light travel. The difference between no atoms and atoms is the difference between a glowing fog and a cosmos that can be seen through. Before atoms, there was also no familiar colour. Colour is not only a property of light, it is a relationship between light, matter, and eyes or instruments. The early universe had radiation with a distribution shaped by its temperature, but there were no surfaces to reflect particular colours, no atoms to absorb and emit light in the characteristic ways that later create spectral fingerprints, and no observers with eyes to call anything red, blue, or golden. Talking about the colour of the pre-atom universe is a little like asking what flavour a thunderstorm has before tongues exist. You might be able to invent an answer, but it would not be very useful, and might worry the meteorologists. There was no sound either, at least not sound as you and I hear it. Sound needs a medium, and the early universe did contain a dense medium that could support pressure waves. In that technical sense, there were oscillations moving through the hot plasma, waves of compression and rarefaction. These early waves later left an imprint on the distribution of matter and radiation. But there were no ears, no air in the earthly sense, and no cosy cosmic hum that could be heard by someone floating nearby. Still, if we translate the idea carefully, the young universe did have rhythms in its density. Matter and radiation pushed and pulled under gravity and pressure. These subtle patterns would help shape where galaxies later formed. Even before atoms, the universe was already carrying the faint outlines of future structure, though not in any way that resembled a picture. Gravity was present, and gravity was patient. While the other forces were busy with particles at tiny scales, gravity cared about energy and density. Tiny differences in density mattered to it. A slightly denser region pulled a little more strongly. But in the earliest hot plasma, radiation pressure resisted collapse. Matter could not simply gather into stars right away. The universe was too hot, too smooth, and too tightly coupled between radiation and charged particles. Gravity had to wait for the right conditions too. It is a recurring theme in this story. Everything important seems to be waiting for the universe to cool enough. Atoms waited, light waited, stars waited, chemistry waited. Even gravity, the great gatherer, had to wait before it could build the first large structures. This can be reassuring in a small human way. The universe did not become interesting all at once. It did not rush from beginning to planets in a single dramatic gesture. It passed through stages where possibilities existed but could not yet be fulfilled. The ingredients for atoms were not all available immediately. When some ingredients appeared, the temperature was still wrong. When nuclei formed, electrons still could not settle. When atoms formed, stars still had to gather. The story is not a straight sprint. It is more like a long sequence of doors opening when conditions finally allow them to open, one after another, without hurry, because the universe has never seemed especially concerned about deadlines. In this pre-atom era, the universe was also much smaller in the sense that distances between regions were far less than they are now. The observable universe today contains galaxies separated by enormous stretches of space. Back then, the material that would become those galaxies was packed far more closely. But it is important not to picture all of today's galaxies as tiny finished objects squeezed together. Galaxies did not yet exist. Stars did not yet exist. It was the material and energy that would later become them, not miniature versions of them. Thinking otherwise is a bit like imagining that an acorn contains a tiny wooden chair, because one day wood from a tree might become furniture. The future is not already assembled inside the past in that literal way. Time itself was also being measured differently, not because time was behaving casually, but because the meaningful events were happening on scales far removed from human clocks. In the earliest periods, major changes occurred in tiny fractions of a second. Later, important transitions took minutes. Later still, hundreds of thousands of years passed before neutral atoms formed in large numbers. A human lifetime feels long to us because we are built from heartbeats, sleep cycles, meals, seasons, and birthdays. The early universe had no such markers. Its clock was temperature, expansion, and interaction. What mattered was not whether it was morning or evening, but whether conditions had cooled enough for the next physical arrangement to survive. No chemistry also means no memory in the biological sense, no life, no records, no witnesses. The early universe did not leave us a diary. It left evidence. That evidence is written in radiation, in the abundance of light elements, in the large-scale structure of galaxies, and in the patterns of the ancient microwave background. We infer the pre-atom universe by combining observations with physical laws tested in many other settings. Particle accelerators recreate tiny, brief versions of some early universe conditions, not by making little universes, thankfully, but by colliding particles at high energies and studying the results. Telescopes look outward, and therefore backward in time, because light takes time to travel. Cosmology is a kind of careful reconstruction. We cannot visit the universe before atoms, but we can read the traces it left behind, and the traces tell a consistent story. There was a time when the universe was too hot for nuclei, then a time when simple nuclei could form, then a much longer period when nuclei and electrons existed separately in a plasma, Then, after enough cooling, electrons combined with nuclei, and the first stable atoms filled space. This is not guesswork in the casual sense. It is supported by measurements of primordial hydrogen and helium, by the cosmic microwave background, and by the way matter is distributed across the universe today. Science does not know every detail of the earliest beginning, and it is honest about that. But the broad outline from hot dense plasma to atoms is one of the great achievements of modern cosmology. Still, it can feel almost backwards. We tend to think of atoms as the basic starting point of matter. In school, atoms are often introduced as the building blocks of everything, and for daily life that is a good working idea. But cosmically, atoms are not the first building blocks. They are later arrangements. They are what the universe made after more primitive forms of matter became possible. Before atoms came particles. Before ordinary particles came energy in forms that could transform into particles. Before stable structures came conditions too intense for stability. The atom is simple compared with a cell or a mountain, but it is sophisticated compared with the earliest universe. The first atom also required the forces of nature to behave in balanced ways. The electromagnetic force allowed electrons and nuclei to attract. The strong nuclear force allowed protons and neutrons to bind into nuclei. Gravity shaped the expansion and later gathered matter. Other processes determined how many particles survived, how matter differed from antimatter, and how the early universe cooled. If any of these ingredients had been very different, the path toward atoms might have changed completely. That does not mean the universe was designed like a clock on a workbench. It means atoms depend on deep physical relationships. Even the simplest hydrogen atom is not just a proton and an electron. It is a stable agreement among the rules of nature. For now, the key point is that the universe before atoms was not waiting in darkness with tiny pieces ready to assemble. It was a hot, dense, opaque plasma, and, before that, even more extreme states where the familiar pieces of matter had not yet formed. It had no chemistry because there were no stable atoms. It had no transparent light because free charge particles scattered radiation constantly. It had no ordinary shape because there were no objects with surfaces, no stars, no galaxies, and no clear boundaries between familiar things. Yet it was not empty and not meaningless. It contained the conditions from which structure would emerge. It contained the early variations that would later grow. It contained energy capable of becoming matter, and matter capable eventually of becoming atoms. As the universe continued expanding, its temperature kept falling. The restless early crowd began to change character. The conditions that once prevented stable particles began to allow them. Quarks that had moved freely became confined inside protons and neutrons. Matter and antimatter met and mostly vanished into radiation, but a small excess of matter remained. That small excess mattered more than almost anything, because without it there would be no protons left to build hydrogen, no nuclei, no atoms, no stars, and no quiet listener. Many billions of years later, considering all this while trying not to check the time, the universe was still far from chemistry, still far from light travelling freely, but the first ingredients of atoms were beginning to appear inside the cooling fire, and the next step is to follow how energy, in that young and crowded cosmos, began to take on the more lasting form we call matter. The universe was still far too young for atoms, but it was no longer quite as impossible to describe as it had been at the very beginning. It was expanding, cooling, and changing with a speed that makes ordinary change feel almost frozen. In everyday life, when something cools, we imagine steam fading from a cup of tea, soup becoming safe enough to sip, or the suspicious patience required before biting into a slice of pizza that has clearly chosen violence. But the cooling of the early universe was not a small loss of warmth. It was a transformation in what reality could be. At the highest temperatures, the universe was not ready for matter in the familiar sense. Energy was everywhere, packed into space so intensely that particles did not behave like calm little beads moving through emptiness. Instead, energy and particles were part of a restless exchange, appearing, disappearing, colliding, changing identity, and refusing to settle into anything that could be called ordinary material. This is the stage where we begin to ask how energy became matter. Not matter as in tables, stones, clouds, or even atoms, but the first lasting particles that could later become the ingredients of atoms. In modern physics, energy and matter are not completely separate categories. They are deeply related. Energy can appear as particles when conditions allow it, and particles can vanish into energy when they meet their opposites. This sounds strange if we think of energy as a kind of invisible fuel and matter as solid stuff. A loaf of bread seems very different from the warmth in an oven. A pebble seems very different from sunlight. But at the deepest level, the universe does not draw the boundary as firmly as our senses do. Matter is not frozen magic. Energy is not ghostly nothing. They are different expressions of physical reality, and in the early universe the border between them was alive with activity. To picture this gently, imagine a very crowded dance floor where no one keeps the same partner for long. Energy gathers into particle pairs. Particles meet and vanish back into radiation. Radiation collides and produces more particles. Nothing stays settled for more than a breath, though of course there were no breaths yet, and certainly no one standing by the wall wondering whether they should join in. The early universe was too hot and too dense for stillness. It was a place where creation and destruction were part of the same ongoing process. Matter did not appear once and then simply remain. It had to survive a storm of interactions long enough to become part of the later universe. A key idea here is that particles often came with partners called antiparticles. For many kinds of matter, there is a matching form of antimatter. An electron has an antimatter partner called a positron. Other particles have their own counterparts. When a particle and its antiparticle meet, they can destroy each other, turning their mass back into energy. And when there is enough energy available, the reverse can happen too. Energy can produce particle and antiparticle pairs. In the early universe, this back and forth happened constantly. Matter and antimatter were not rare curiosities kept safely in special laboratories. They were part of the basic early weather of existence. This raises one of the most important questions in all of cosmology. If energy created matter and antimatter together, and if matter and antimatter destroy each other when they meet, why is there anything left? Why did the universe not end up as a sea of radiation with no matter remaining at all? Why are there protons, electrons, atoms, stars, planets, and people, instead of only light and a rather disappointing absence of furniture? The answer, as far as we can tell, is that the early universe had a tiny imbalance. For reasons still not fully understood, matter gained the smallest advantage over antimatter. For every huge number of matter and antimatter particles that met and vanished, there was a tiny excess of matter left behind. That leftover matter became everything we know. It is difficult to overstate how important that slight imbalance was. Almost all the matter and antimatter in the early universe may have annihilated into radiation, but not quite all of it. The small remainder became the raw material for protons, neutrons, electrons, atoms, stars, planets, oceans, and living cells. Your hand, your breath, the air in the room, the walls around you, and the dust that appears under furniture with a confidence nobody invited, all exist because matter slightly outlasted antimatter. The universe as we know it is made from the leftovers of an ancient imbalance. It is a humbling thought. We are not made from the main feast, so to speak, but from what remained after the first great cancellation. Scientists call the process that produced this imbalance baryogenesis, though the name is much less soothing than the idea is profound. It refers to the origin of the excess of matter over antimatter. The details remain an open area of research. We know that the laws of physics must allow certain differences between matter and antimatter, because otherwise the balance would have stayed perfect and nothing material would remain. We also know that the early universe went through conditions far beyond anything we can fully recreate. Particle accelerators can give us glimpses of high-energy behaviour, and they have shown that matter and antimatter are not always treated with perfect symmetry. But the full explanation for why matter survived is still incomplete. It is one of those scientific mysteries that sits quietly at the foundation of everything, like a loose thread in the universe's oldest sweater. During this early time, the universe was filled with many kinds of particles, some familiar, some more exotic and short-lived. The particles that matter most for the atom story include quarks, electrons, neutrinos, photons, and the forces that allowed them to interact. Quarks would later be locked inside protons and neutrons. Electrons would later be captured into atoms. Photons, the particles of light, would continue to fill the universe and carry energy. Neutrinos, ghostly and almost indifferent to ordinary matter, would stream through space with remarkable freedom. The early universe was not simple in the sense of being empty. It was simple in the sense that it had not yet built larger structures. It was rich in basic ingredients but poor in stable arrangements. At extremely high energies, the forces of nature may have behaved differently from how they behave today. Some forces that now appear distinct may once have been united in a deeper way. As the universe cooled, these forces separated into the forms we now observe. This is not separation like people leaving different exits after a concert. It is more like water freezing into ice, where a change in temperature produces a change in the structure of what is possible. Physicists describe these early changes as phase transitions. We know phase transitions from daily life, even if we do not usually use the term while waiting for the kettle. Water becomes steam. Water becomes ice. Butter softens in a warm kitchen. Chocolate melts at exactly the wrong moment inside a pocket. The early universe also changed state as it cooled, though on a scale and with consequences far beyond any kitchen accident. These transitions mattered because they shaped the properties of particles and forces. The universe we inhabit has a certain set of particles with certain masses, charges and interactions. Those features were not useful for atoms until the universe had cooled into a stable pattern of physical laws. If the particles had no rest mass, or if the forces did not behave as they do now, the later formation of protons, nuclei and atoms would not proceed in the same way. The first atom depended on these earlier transitions, even though atoms themselves were still far in the future. Before the first atom could exist, the universe had to become the kind of universe in which particles could have stable identities. The phrase energy became matter can sound as if energy decided to harden into little pellets. That is not quite right. In quantum field theory, which is our most successful language for describing particles, particles are excitations of underlying fields. A field is something that exists throughout space, and a particle is a particular kind of disturbance in that field. This can sound abstract, but there is a familiar comparison. A ripple on a pond is not a separate object placed on top of the water, it is a pattern in the water itself. In a somewhat similar way, a particle is a pattern in a field. The early universe was full of such patterns, constantly forming and interacting. Matter was not being carved out of emptiness like clay from a block. It was emerging as stable activity in the fields that make up physical reality. This also helps explain why nothing is a difficult word. In quantum physics, even what we call empty space is not a blank absence. Fields remain, the rules remain, possibilities remain. At the very beginning, we do not know whether the words space and time apply in the ordinary way, but once we're discussing quantum fields and particles, we're already dealing with something physical. The first flicker of matter was not a rabbit pulled from a hat labelled absolute nothing. It was energy in the young universe taking forms that could become particles, and a tiny surplus of matter surviving when most matter and antimatter vanished back into radiation. That is less like a magic trick and more like a balance scale that almost, but not quite, returns to zero. For a while, the universe was so hot that massive particles could be produced easily from energy. But expansion changed everything. As the universe grew, it cooled, and the average energy of radiation fell. Eventually, there was not enough energy constantly available to recreate certain particle pairs after they annihilated. When that happened, many heavy particles disappeared from the everyday population of the universe. They could still exist briefly in high-energy events, but they no longer filled space in great numbers. One by one, as the temperature dropped, the early universe lost the ability to casually produce its heavier particles. The particle crowd thinned and simplified. The universe was not becoming empty, but it was becoming more selective. This selecting process is important. The universe did not choose in the human sense, of course. It did not look at a menu and decide to keep electrons while sending something else back to the kitchen. Rather, the cooling conditions determined which particles could remain abundant. Some particles were unstable and decayed into lighter ones. Others annihilated with their antimatter partners. Some, like photons and neutrinos, persisted in enormous numbers. A tiny excess of matter particles survived. By the end of this early sorting, the ingredients that would later matter most included electrons and quarks that would become locked into protons and neutrons. The road to atoms was still long, but the first durable pieces of the road were appearing. Electrons are especially important in this story, because an atom is not just a nucleus. Without electrons, a nucleus is only a positively charged centre. Electrons give atoms their size, their chemistry, and their ability to bond with other atoms. But in this early period, electrons were still free. They were not orbiting nuclei. There were no atoms to orbit. They moved through the hot plasma among radiation and other particles. Electrons also had antimatter partners, positrons, and many electron-positron pairs annihilated as the universe cooled. Yet enough electrons remained to balance the positive charge of the protons that would later form. This balance was essential. A universe with the wrong charge balance would be a very different place, and probably not one where atoms calmly form and later gather into clouds, stars, and sleepy people thinking about atoms. The quarks had their own destiny. Quarks carry a kind of charge related to the strong nuclear force. They interact through gluons, which bind them together. At very high temperatures, quarks and gluons moved freely in a quark-gluon plasma. But as the universe cooled, the strong force confined quarks into composite particles. This was a major turning point. Quarks became trapped inside protons and neutrons, the particles that later form atomic nuclei. The universe passed from a state where the ingredients of nuclei moved freely into one where the basic nuclear building blocks existed. Again, the first atom was not present yet, but the future nucleus of hydrogen, a proton, was beginning to become possible. The simplest hydrogen nucleus is just a single proton. In that sense, once protons existed, one crucial ingredient for the first atom was already present. But a proton alone is not yet hydrogen as an atom. It is a bare nucleus, positively charged and surrounded by a universe still far too hot for an electron to settle down with it. Still, the appearance of protons was an enormous step. Protons are stable, or at least stable for all practical cosmic purposes as far as we know. They could survive through the long wait ahead. Neutrons, by contrast, are stable when bound inside nuclei, but unstable when alone. Free neutrons decay over time. This difference would later affect how many hydrogen and helium nuclei formed in the first minutes of the universe. The early universe was therefore a place of both violence and preparation. Particles collided with tremendous energy. Matter and antimatter annihilated. Heavy particles vanished. Quarks became confined. Electrons survived. Photons filled space. Neutrinos slipped away into their own quiet history. To us, it may sound chaotic, but to physics it was a sequence of lawful changes. Each stage followed from the temperature, density, expansion rate, and interactions of particles. The universe was not assembling matter with little tools. It was changing conditions, and matter emerged because under those conditions certain forms became stable enough to last. There is something almost funny about how far this is from our usual idea of making something. When humans make things, we gather materials first. Flour before bread, bricks before a wall, Spare screws before a drawer that somehow still wobbles. But the universe had to make the materials themselves. It had to produce the particles that would later count as ingredients. Before there could be hydrogen, there had to be protons and electrons. Before protons, there had to be quarks bound together. Before stable quarks in protons, there had to be energy and fields in the hot early universe. The supply chain of existence is rather long, and unlike most supply chains, it begins before there are boxes, labels, roads, or anyone to complain about delivery times. As cooling continued, the balance between creation and destruction shifted. Earlier, energy was high enough that particle pairs could be recreated after annihilation. Later, that became harder. Annihilation still happened, but recreation became less common for many particle types. This is why the small matter excess became so important. If matter and antimatter had been exactly equal, almost everything would have vanished into photons. But because matter had the slightest surplus, after the annihilations there was matter left over. Not much compared with the radiation, but enough. Enough to become the cosmic material from which all later structure would be built. The universe did not need a large imbalance. It only needed a small one, multiplied across everything. This surviving matter was not yet arranged into atoms, but it had begun to have identity. Protons were protons, neutrons were neutrons, electrons were electrons. These particles could participate in the next major stage, when protons and neutrons began to form simple atomic nuclei. But even that stage had to wait until the universe cooled further. If protons and neutrons tried to bind too early, high-energy photons could blast the nuclei apart. Once again, the universe needed the right temperature, neither so hot that structure was destroyed immediately, nor so cool that the necessary interactions became too rare. It is a delicate timing, though no clockmaker was standing nearby with a clipboard. The expansion rate of the universe set the pace. The fact that matter emerged from energy does not mean matter is an illusion. Matter is real. Your pillow is not a philosophical rumour. The floor is not a suggestion, as anyone who has stubbed a toe can confirm with impressive clarity. But matter is not as separate from energy as it appears in everyday life. At deep levels, mass, energy, fields, and particles belong to the same physical story. The early universe reveals this relationship because conditions were extreme enough for the transformations to be common. Today, under ordinary conditions, we do not see teacups turning into radiation, or sunlight becoming new particles on the breakfast table, which is probably for the best. The energies are too low, and stable matter remains stable. But in the earliest universe, the everyday distinction had not yet settled into the calm form we know. This is why physicists look to high-energy experiments to understand the early universe. Particle colliders accelerate particles to enormous speeds and smash them together, concentrating energy into tiny regions. For brief instants, this allows heavy particles to appear, and it reveals patterns that help us infer how matter behaved when the universe was young. A collider is not recreating the entire Big Bang, despite what dramatic headlines sometimes suggest. It is more like recreating tiny fragments of high-energy behaviour, controlled and measured with extraordinary care. From these fragments, scientists learn how particles interact, how symmetries can break, and why the early universe may have evolved the way it did. It is a bit like studying sparks to understand a fire that once filled everything, except with more mathematics, larger machines, and fewer marshmallows. The first flicker of matter was therefore not a single flash in one place. It was a universe-wide process. Everywhere, as space expanded and cooled, energy and particles interacted. Everywhere, matter and antimatter nearly erased each other. Everywhere, a tiny excess of matter remained. Everywhere, quarks eventually became confined into protons and neutrons. Everywhere, the universe moved one step closer to having the pieces from which atoms could later be made. There was no central workshop, no preferred location, no little cosmic factory at the edge of space. The entire observable universe was the factory, if we may use such an unreasonably practical word for something so enormous. It is also important to say that we do not yet understand everything about this period. The broad picture is strong, but some details remain mysterious. The origin of the matter-antimatter imbalance is not fully solved. The exact physics of the earliest moments may require theories beyond the ones we currently have. The connection between quantum physics and gravity is still incomplete. There may have been particles and processes in the early universe that we have not yet discovered. Science is not a finished book sitting neatly on a shelf. It is a working investigation, with some pages clear, some smudged, and some still sealed. But the story we can tell is already remarkable. Matter did not have to survive. Yet, it did. And because it did, the first atom became possible. By the time this stage had unfolded, the universe had changed from an almost unimaginable high-energy state into something still intensely hot, but more organized. The surviving matter was a tiny residue compared with the ocean of radiation, but it was enough. Protons and neutrons existed. Electrons existed. Photons still filled space in overwhelming numbers. Neutrinos streamed through the cosmos. There were not yet nuclei beyond the simplest possibilities in any lasting abundance, and there were certainly no atoms. But the earliest raw ingredients were now available. The first flicker had become a more persistent glow. From here, the story moves toward the hearts of atoms. Before an electron can join a nucleus, the nucleus must exist. Before the universe can make neutral hydrogen, it must have protons. Before it can make helium atoms, it must first bind protons and neutrons into helium nuclei. This next step happened while the universe was still very young, in a period when the temperature had fallen enough for nuclear particles to combine, but not so low that the reaction stopped entirely. It was a brief window, a cosmic interval in which the first nuclei formed from the surviving matter. The universe still had no chemistry, no transparent light, and no stable atoms. But within its cooling plasma, the central cores of the first atoms were beginning to take shape, and the long road from raw energy to ordinary matter moved quietly onward. At this point in the young universe, matter had survived its first great test, but it still did not look anything like the matter around you now. There were no atoms, no nuclei in the familiar sense, no molecules, no grains of dust, no gas clouds drifting through space. Even protons and neutrons, the sturdy little centers of future atoms, had not always existed as separate stable particles. They too had to be made. And before they could appear, the universe passed through a stranger and more restless stage, a time when their smaller ingredients moved freely through an unimaginably hot cosmic soup. Those ingredients are called quarks, and if atoms are the letters of ordinary matter, then quarks are more like the strokes of ink that will eventually help form the letters. They are not things we meet directly in daily life. You will not find a loose quark hiding under the sofa, even if the sofa has collected enough crumbs to qualify as a small geological formation. Quarks are usually confined inside larger particles, bound so tightly that they do not wander around alone in the world we know. But in the earliest universe, before protons and neutrons settled into existence, quarks moved in a freer, hotter, denser state, and that state was one of the necessary steps on the road to the first atom. To understand why quarks matter so much, we need to remember what an atom will eventually need. The simplest atom, hydrogen, needs a proton and an electron. The electron gives the atom its outer behavior, its ability to interact chemically, its size in the everyday atomic sense. The proton gives it the positive center. More complicated atoms need nuclei made of protons and neutrons together. So before atoms can form, there must be protons and neutrons. Before protons and neutrons can form, quarks must be bound together. This means that the story of the first atom passes through a time when the universe was not building atoms yet, or even atomic nuclei, but was preparing the particles that would later become the cores of atoms. It is like trying to tell the story of a house by beginning with bricks, only to discover that before the bricks there was clay, and before the clay there was dust, minerals, water, pressure, heat, and someone eventually saying, perhaps we should make bricks. The universe did not make atoms from finished parts, it made the parts too. Quarks are fundamental particles, at least as far as our current understanding goes. That means we do not know of any smaller pieces inside them. They are not tiny balls in the ordinary sense, though it is hard for the mind not to picture them that way. We like little objects. We like beads, pebbles, seeds, and grains of salt. But quantum particles do not behave like miniature pebbles with crisp surfaces. They are excitations of fields, patterns of physical reality that carry certain properties. Still, when we speak gently and carefully, it is useful to say that quarks are among the basic ingredients from which protons and neutrons are made. The proton contains quarks arranged in one way. The neutron contains quarks arranged in another. These arrangements are held together by the strong nuclear force, one of the fundamental forces of nature, and it is strong for a reason. It has the task of binding pieces together inside the heart of matter, where the electromagnetic force would otherwise make positively charged particles push away from each other. The strong force is not like gravity, which reaches gently across cosmic distances and gathers stars, planets, and galaxies. It is not like electromagnetism, which gives us light, chemistry, electricity, magnets, and the mild panic of realizing your phone battery is at 1%. The strong force works on incredibly small distances, and within that tiny range it is extraordinarily powerful. It binds quarks together into protons and neutrons. Later, it also helps bind protons and neutrons together inside atomic nuclei. Without it, the universe could not build the centers of atoms. There would be no stable nuclei, no hydrogen in the form we know, no helium, no carbon, no oxygen, no chemistry, no water, and no one getting comfortable under a blanket while considering the early universe. Quarks come in different types, which physicists call flavors. The name flavor is one of those charming moments when physics borrows a word from ordinary life and then uses it for something that has absolutely nothing to do with soup, sweets, or whether a biscuit goes well with tea. The quarks that matter most for ordinary protons and neutrons are called up quarks and down quarks. Heavier quarks exist too, but they are unstable and do not last in the ordinary matter around us. In the early universe, when energies were far higher, heavier particles could appear more readily, and the particle population was richer and more varied. But as the universe expanded and cooled, heavier particles decayed or vanished from the common scene, leaving the lighter and more stable ingredients that would go on to shape the matter we know. The earliest quark-filled universe was not a calm collection of little parts waiting to snap together like pieces in a toy set. It was a seething plasma of quarks and gluons. Gluons are the particles associated with the strong force. They carry the interaction that binds quarks, and they are named because they help glue quarks together, which is refreshingly direct by physics standards. In the quark-gluon plasma, quarks and gluons were not locked inside protons and neutrons. They moved through a dense, hot state where the usual boundaries of those particles had not yet formed. It was not soup in the kitchen sense, of course. There were no onions, no steam, no wooden spoon, and no one asking whether it needed more salt. But the word soup gives a useful feeling of many ingredients mixed together in a hot fluid state, before they separate into more familiar forms. This quark-gluon plasma was incredibly hot, hotter than the core of any star today, hotter than anything that could survive as an object. But temperature here does not simply mean warmth. It means energy, motion, and the ability of particles to appear, vanish, collide, and transform. At such extreme energy, the strong force behaved differently from how it behaves inside matter today. Quarks were not yet confined in the same way. They could move through the plasma, interacting constantly with gluons and with each other. The universe was expanding all the while, and expansion brought cooling. As the temperature fell, a transition occurred. Quarks became confined. They were locked into composite particles. The main survivors relevant to atoms were protons and neutrons. This transition is one of the great changes in the early universe. Before it, the universe had free quarks and gluons in a dense plasma. After it, the universe had hadrons, which are particles made of quarks bound together. Protons and neutrons are examples of hadrons. The process is sometimes called hadronization, another word that may not sound especially sleepy, but the idea behind it is essential. The universe cooled enough that quarks could no longer roam freely through the plasma. They grouped into stable combinations. The future centers of atoms began to exist as recognizable particles. The universe had not yet made nuclei in abundance, and it certainly had not yet made atoms, but it had crossed a threshold. It now had protons and neutrons, and with them the possibility of atomic nuclei. It is worth slowing down here because confinement is a very unusual feature of the strong force. With gravity or electromagnetism, we are used to forces becoming weaker as objects move farther apart. Pull two magnets apart and the attraction or repulsion weakens. Move away from Earth and gravity weakens. But quarks are not like two magnets that can simply be separated and placed on opposite sides of a desk. As quarks are pulled apart, the strong force does not let them drift freely into isolation. The energy in the field between them grows, and instead of producing a lonely quark, the system tends to create new particle pairs. The result is that quarks remain confined inside composite particles. It is as if nature has decided that quarks may attend the party, but only in groups, and any attempt to make one leave alone results in more guests arriving. This is not a perfect image, but it captures the strange stubbornness of the situation. Because of confinement, the quarks inside you today are not accessible as separate objects. They are inside protons and neutrons in the nuclei of your atoms. Those nuclei sit at the centers of atoms in your body, in the bed beneath you, in the glass of water nearby, and in the air moving gently through the room. The quarks themselves are hidden deep within. You do not experience them directly. You experience the large-scale consequences of their being bound together. The solidity of matter, the existence of nuclei, the stability of atoms, and the chemistry of life all depend in part on the fact that quarks are bound in just this way. The early universe had to pass from quark freedom to quark confinement for the ordinary world to become possible. At this stage, we should also notice that protons and neutrons are similar but not identical. Both are made of up and down quarks, but in different combinations. A proton has a positive electric charge. A neutron has no overall electric charge. That small difference matters enormously. Protons can attract electrons and become the center of hydrogen atoms. Neutrons, when bound with protons, help stabilize larger nuclei. Without neutrons, building elements beyond hydrogen would be very difficult, because protons repel other protons electrically. Neutrons add strong nuclear binding without adding positive electric charge. They act a little like quiet companions in the nucleus, not neutral in importance, just neutral in charge. Later, when the first nuclei form, neutrons will help create helium and small traces of other light nuclei. But during the quark soup stage, even neutrons were still waiting for their own assembly. Once quarks became bound into protons and neutrons, another kind of balance became important. In the hot early universe, protons and neutrons could transform into one another through interactions involving the weak nuclear force. This force is responsible for certain kinds of particle change and radioactive decay. It is weaker than the strong force, but it plays an essential role in shaping the early particle population. While the universe remained very hot, protons and neutrons could swap identities through these interactions. As the universe cooled, these conversions became less common, and the relative numbers of protons and neutrons began to settle. That later balance would determine how much hydrogen and helium formed in the first few minutes. This may sound like a small accounting detail, but the universe is built from such details. If there had been many more neutrons, more helium could have formed. If there had been far fewer, the early element mixture would have been different. the first stars would have formed from different starting material. The later history of galaxies and chemistry might have shifted. The amount of helium made in the early universe is one of the key pieces of evidence supporting the hot Big Bang model. Scientists can measure the abundance of light elements and compare it with predictions. The numbers agree remarkably well, which is one reason cosmologists are confident that the early universe really did pass through these stages. The ancient quark soup is not just a fanciful image, it is part of a chain of evidence connecting particle physics to the matter we observe today. Still, the quark-gluon plasma itself is not only a thing of the distant past. Scientists have recreated tiny droplets of it in particle accelerators by colliding heavy atomic nuclei at tremendous energies. For an instant, the conditions are hot enough to free quarks and gluons from their usual confinement inside protons and neutrons. These tiny fireballs expand and cool almost immediately, and physicists study the particles that emerge to infer what the plasma was like. This does not recreate the whole early universe, of course. It is more like producing a spark from a vanished cosmic furnace. But it tells us something remarkable. The quark-gluon plasma seems to behave less like a thin gas and more like an almost perfect fluid, flowing with extremely low resistance. The early universe, at least during this stage, may have had a kind of fluid character, not a soup with chunks, but a smooth, dense, strongly interacting state. There is a quiet beauty in that. Before matter became grainy in the way we imagine particles, before atoms gave the universe its later texture, there was a hot, dense fluid of fundamental ingredients. It was not empty, and it was not yet structured. It was active, governed, changing. From that fluid emerge protons and neutrons, particles so stable that many of the protons formed in the early universe still exist today. The hydrogen nuclei that later became part of stars, water, and living things trace their ancestry back to this transition. A proton in your body may be ancient in the deepest possible sense, not merely older than Earth or older than the Sun, but born when the universe was less than a blink old by human standards. It has been through stars, clouds, planets, and biology, but its basic identity as a proton began in that first cooling. One of the difficult ideas here is that the universe did not become less interesting as it cooled. It became more capable of structure. Extreme heat can create variety, but it can also prevent things from lasting. Cooling allowed certain patterns to become stable. Quarks bound into protons and neutrons. Later, protons and neutrons would bind into nuclei. Later still, electrons would bind to nuclei as atoms. At each stage, the universe became less violently energetic and more able to preserve form. It is tempting to think of cooling as a loss, because in daily life, warm things feel lively and cold things feel still. But in cosmology, cooling was creative. It opened doors. It allowed the universe to keep what it made. The quark stage also reminds us that the first atom did not come directly from nothing in one leap. It came through layers of emergence. The universe did not move from absolute absence to hydrogen in a single step. First, there was a hot, dense physical state. Then energy-populated fields with particles. Matter gained a tiny advantage over antimatter. Quarks and gluons filled the early plasma. Quarks became confined into protons and neutrons. Protons and neutrons later formed nuclei. Electrons eventually joined those nuclei. The atom is simple, but its history is not. Even the simplest atom carries within it the memory of many earlier transformations, though not memory in the way a mind remembers. It carries the consequences of those transformations in its very structure. For a sleepy comparison, imagine waking up to find a loaf of bread on the table and asking where it came from. A quick answer might be, from the bakery. A better answer would include flour, water, yeast, salt, heat, time, grain, soil, sunlight, rain, farming, milling, and perhaps one baker who woke up earlier than seems reasonable. The atom is like that. We can say a hydrogen atom is a proton and an electron, and that is true. but the proton came from quarks. The quarks belonged to fields in a hot early universe. The electron survived the matter-antimatter era, and the conditions that allowed them to bind arrived only after long cosmic cooling. The short answer is accurate. The long answer is the story. There is also a humbling scale difference. Quarks are tiny beyond imagination, yet their behaviour shaped the entire cosmos. The large-scale universe of galaxies depends on the small-scale rules of particle physics. If quarks did not bind as they do, protons and neutrons would not exist as they do. If protons and neutrons did not exist, there would be no atomic nuclei. If no nuclei, no atoms. If no atoms, no stars in the familiar sense, no planets, no chemistry, no life. The largest structures we see through telescopes are connected to interactions far smaller than anything a microscope could ever show directly. The universe is stitched together across scales, from quarks to clusters of galaxies, and the thread is physical law. During the quark-gluon stage, there was still no light travelling freely. Photons were present in huge numbers, but the universe remained a dense interacting plasma. Any light was constantly scattered. There were no atoms to produce the familiar lines of atomic spectra, no transparent space through which ancient light could simply cross. There was also no chemistry, because chemistry requires electrons arranged around nuclei. The creation of protons and neutrons was necessary but not sufficient. It gave the universe nuclear building blocks, not chemical ones. This distinction is important because it helps us avoid rushing the story. The universe often gives us ingredients long before it gives us the finished dish, and in this case, it still had several courses to prepare. As protons and neutrons emerged, most of the antimatter had already disappeared through annihilation with matter, leaving that tiny excess of matter behind. Protons had antimatter counterparts called antiprotons, and neutrons had antineutrons. In the early particle crowd, these would have annihilated with their matter partners when they met. But the matter excess meant some protons and neutrons remained after the great annihilations. The universe now contained a small but crucial population of baryonic matter, the kind of matter that would eventually form atoms. It was small compared with the number of photons, but it was enough. This is another recurring lesson. The universe did not need much leftover matter to build everything visible. It needed a little, spread across vast space, and gravity would later do patient work with it. Neutrons, however, faced a problem. A free neutron is not stable forever. Left alone, it will decay into a proton and other particles. This meant that the timing of the next stage mattered. If the universe waited too long before forming nuclei, too many neutrons would decay, and less helium would be made. But the universe also could not form stable nuclei too early, because high-energy photons would break them apart. There was a window when the temperature had fallen enough for nuclei to survive, while enough neutrons still remained to join with protons. The quark soup had produced the necessary building blocks, but the next stage depended on a careful balance between cooling, expansion, reaction rates, and decay. No one was adjusting dials. The universe simply followed its laws, and the result was the first nuclear matter. Even though this all happened in a tiny fraction of the universe's early history, it set the tone for everything that followed. The protons formed then are central to hydrogen, the most abundant element in the universe. Hydrogen would later gather into clouds, collapse under gravity, ignite stars, and provide the fuel for stellar fusion. Neutrons, bound in helium and later in heavier elements, would help build the diversity of matter. The strong force that confined quarks also made nuclei possible. The properties of quarks influence the masses of protons and neutrons, which influence nuclear reactions, which influence the chemical future of the cosmos. The first atom was still far away in time, but the shape of its possibility was already being drawn. So in the hot early universe before protons and neutrons, the story passes through a fluid state of quarks and gluons. This was not a decorative detail, not an optional prelude, but the stage in which the cause of future atoms became possible. Quarks, once free in the dense early plasma, became confined as the universe cooled. They formed protons and neutrons. Protons provided the centres of future hydrogen atoms. Neutrons made possible the first helium nuclei and later the stability of heavier nuclei inside stars. From a restless soup of tiny ingredients came the first durable particles of ordinary matter. The universe still had no atoms, no chemistry, and no clear light. But it had crossed from raw particle possibility into the beginning of nuclear structure. The next change would be just as important and in a way more familiar. Once protons and neutrons existed, they could begin to bind with one another. Not into atoms yet, because electrons were still too energetic to settle around nuclei, but into the first atomic nuclei themselves. The hearts of hydrogen were already present in the form of lone protons. The hearts of helium would soon form from protons and neutrons joined together. For a brief interval, while the universe was still hot but no longer too hot, nuclear reactions would build the first simple nuclei from the surviving matter. The universe was still a glowing plasma, still opaque, still far from chemistry, but inside that plasma the centres of the first atoms were beginning to form, and the long wait for full atoms moved one careful step closer. By now, the young universe had already done something extraordinary. It had taken energy, activity, imbalance, and cooling, and from that restless beginning, it had produced the first lasting pieces of ordinary matter. Quarks had become trapped inside protons and neutrons. Electrons were present too, though still far too energetic to settle down into atoms. Photons filled everything like a thick glowing storm. Neutrinos were already slipping through the cosmos with their usual talent for barely noticing anything in their way. The universe was still much too hot for chemistry, much too dense for clear light, and much too simple for stars or planets. But it had reached a new possibility. It now had the pieces needed to build the hearts of atoms. An atomic nucleus is the central core of an atom. Later, when electrons are able to join it, the nucleus will become the anchor around which the atom takes shape. But at this moment there are no complete atoms yet. There are only free protons, free neutrons, loose electrons, and radiation. The first great question is whether the protons and neutrons can begin to hold together. If they can, the universe can make the first nuclei. If they cannot, then matter remains a thin crowd of separate particles, all dressed up for chemistry with absolutely nowhere to go. The simplest nucleus is just one proton. In that sense, the nucleus of hydrogen already existed as soon as protons existed. A lone proton is the heart of ordinary hydrogen. It does not yet make a full hydrogen atom because it still needs an electron attached to it. But the central piece is there. Hydrogen, the simplest element, begins with that single positive particle. It is wonderfully modest. No grand architecture, no crowded nucleus, no complicated arrangement. Just one proton, waiting for the universe to cool enough that an electron can finally stay nearby. You might think of it as the smallest possible invitation to chemistry, though the party itself would not begin for a very long time. But the universe did not only make hydrogen nuclei, it also made helium nuclei, along with tiny traces of a few other light nuclei. This early nuclear building period is one of the most important stages in cosmic history. Scientists call it primordial nucleosynthesis, meaning the formation of the first atomic nuclei in the early universe. The name sounds rather formal, as if the cosmos had applied for a certificate, but the idea is simple enough. Once the universe cooled to the right range, protons and neutrons could begin sticking together in stable combinations. Not all combinations worked. Not all attempts survived, but some did, and those successes gave the universe its first nuclear ingredients. The timing was delicate, too early, and the universe was still flooded with radiation energetic enough to break apart any small nucleus almost immediately after it formed. A proton and a neutron might join, only to be struck apart by a photon before they had the slightest chance to look proud of themselves. Too late, and many free neutrons would have decayed. Unlike protons, free neutrons do not last indefinitely on their own. When they are bound inside nuclei, they can be stable, but when they wander alone, they eventually change into other particles. So the universe had to cool enough for nuclei to survive, while still keeping enough neutrons available to build them. It was not planning, of course. The universe was not checking a kitchen timer, it was simply following its laws. But from our point of view, the timing looks almost like a narrow window, opening in a very hot wall. The first key step was making a nucleus called deuterium. Deuterium is a form of hydrogen, but instead of just one proton at its center, its nucleus contains one proton and one neutron bound together. It is often called heavy hydrogen because it behaves chemically like hydrogen later on, but its nucleus is heavier. Deuterium was a necessary stepping stone. Without it, larger light nuclei could not form efficiently. Protons and neutrons needed to pair up before they could move on to build helium, but deuterium was fragile. In the earliest moments when nuclear reactions might have tried to begin, the radiation was still so energetic that deuterium nuclei were quickly broken apart. This delay is sometimes described as a bottleneck. The universe had the ingredients, but the first little bridge between them kept being knocked down. Eventually, as expansion continued, the radiation lost enough energy that deuterium could survive. Once that happened, nuclear construction moved quickly. Deuterium nuclei could collide with protons and neutrons. Further reactions could build helium nuclei. The most stable and important result was helium with 2 protons and 2 neutrons in its nucleus. This became the second most abundant atomic nucleus in the universe after hydrogen, and it is still with us. Much of the helium in the cosmos today was made in that early period, long before stars began making more inside their cores. There is something quietly astonishing about this. The helium that lifts balloons, cools scientific instruments, and makes voices sound briefly ridiculous when inhaled unwisely, has part of its origin in the first few minutes of cosmic history. It was not produced in a laboratory, not originally. It was made when the universe itself was young, hot, and dense enough for nuclear reactions to occur everywhere. Of course, please do not inhale helium from balloons as a pastime. The universe worked very hard to make that helium, and it would be polite not to use it to deprive your brain of oxygen for a party trick. The first nuclei formed not in stars, but before stars. That is an important point, because many people learn that stars make the elements, and that is true for most heavier elements. Stars are the great furnaces that later build carbon, oxygen, nitrogen, silicon, iron, and many other atoms essential for planets and life. But stars did not exist yet. The early universe itself made the simplest nuclei before there were stars to do any stellar cooking. It made mostly hydrogen nuclei, a lot of helium nuclei, a little deuterium, a little helium of another lighter kind, and tiny traces of lithium. That was almost the whole recipe at first. The universe began its chemical future with a very short shopping list. This limited result tells us something important about the early universe. Nuclear reactions require the right conditions, but those conditions did not last long. The universe was expanding and cooling too quickly for heavier nuclei to form in large amounts. There were also gaps in the stability of possible nuclei that made it difficult to build steadily upward from the lightest elements. In stars much later, gravity would hold matter together at high temperature and pressure for millions or billions of years, giving nuclear reactions time to proceed in deeper and more complex ways. But the early universe had only a brief window. It made what it could, then the window closed. After that, the cosmos would have to wait for stars to continue the work. This early nuclear period left behind a pattern we can still measure. The proportions of hydrogen, helium, and other light nuclei are not random. They depend on the temperature, density, expansion rate, and particle content of the young universe. When scientists calculate what should have formed under those conditions, the predictions match observations remarkably well. The amount of helium in ancient gas clouds, the amount of deuterium in distant regions, and the general dominance of hydrogen all point back to this early nuclear stage. It is one of the great successes of cosmology. We cannot watch the first nuclei forming directly, but the universe kept the receipts, which is considerate of it. though perhaps a little smug. The balance between protons and neutrons mattered greatly. Earlier, when the universe was hotter, protons and neutrons could transform into each other through interactions involving the weak nuclear force. As the universe cooled, those transformations became less frequent and the ratio began to settle. Then, as time passed, some free neutrons decayed before they could be captured into nuclei. By the time deuterium could survive, the number of neutrons available helped determine how much helium could form. Since a helium nucleus needs 2 neutrons along with 2 protons, the supply of neutrons acted like a limiting ingredient. If you have ever begun baking and discovered you have far less butter than you thought, you understand the basic emotional tone, though not the temperature. Most neutrons that survived long enough ended up in helium nuclei. This is because helium with 2 protons and 2 neutrons is very stable. Once deuterium could survive, the path toward helium was efficient. The universe turned much of its available neutron supply into helium. The leftover protons remained mostly as hydrogen nuclei. That is why hydrogen is so abundant. There were many more protons than neutrons, and a single proton is already a hydrogen nucleus. It did not need to find a neutron to count as the heart of an atom. It only needed an electron later. This is one reason hydrogen became the primary fuel for the first stars. After the first nuclei formed, the universe was filled mostly with hydrogen nuclei and helium nuclei, along with electrons and radiation. Much later, when the universe cooled enough for atoms to form, those hydrogen-helium nuclei captured electrons. Later still, gravity gathered the neutral gas into clouds. Hydrogen, being abundant and simple, became the main ingredient of the first stars. Inside those stars, hydrogen nuclei fused into helium, releasing energy and lighting the universe. In a sense, the early universe made hydrogen nuclei first, and then stars spent their lives transforming some of that hydrogen into heavier forms. The first nuclear work made the later stellar work possible, but at the time the first nuclei formed, nothing looked like a star. There were no glowing spheres, no galaxies, no constellations, no night sky. The universe was still a hot plasma. The newly formed nuclei were positively charged, and the electrons were still moving freely among them. Radiation still scattered again and again from charged particles. The universe remained opaque. It had the hearts of atoms, but not atoms themselves. It had the centres around which electrons would later gather, but the conditions were not yet gentle enough for that gathering to last. This distinction can feel odd because in daily life we rarely meet bare atomic nuclei. Matter around us is made of complete atoms or ions within certain conditions, and usually the electrons are involved in making materials behave as they do. The nucleus is hidden deep inside. It contains almost all the mass of the atom, but it occupies only a tiny central region. The electron arrangement gives the atom its size and chemistry. The nucleus gives the atom its identity as an element. The number of protons in the nucleus determines whether it is hydrogen, helium, lithium, carbon, oxygen, or something else. In the early universe, those identities existed only as nuclei, not yet as full atoms. Hydrogen and helium were present in a nuclear sense, but chemistry was still asleep. The first nuclei were also formed under conditions very different from nuclear reactions in stars. Stars are held together by gravity. Their cores maintain high temperature and pressure over long periods. They can fuse nuclei steadily, step by step, depending on the star's mass and life stage. The early universe, by contrast, was expanding everywhere. Its density was falling. Its temperature was dropping. Nuclear reactions happened during a short cosmic interval, then mostly stopped. After that, the universe became too cool and too thin for widespread fusion. This is why the early universe did not simply keep building heavier and heavier nuclei. It did not have the time, density, or conditions needed. The first nuclear factory opened briefly, produced mostly hydrogen and helium, made a little else, then closed before anyone could ask for carbon. And carbon would have to wait a very long time. So would oxygen, nitrogen, phosphorus, calcium, iron, and the other elements that make planets and bodies possible. Those would be forged later in stars and stellar explosions. The early universe was chemically poor by later standards. It had almost no heavy elements. Astronomers sometimes call all elements heavier than helium metals, which is deeply confusing if you are thinking of oxygen or carbon, neither of which behaves much like a spoon. But in astronomy, this shorthand is useful. The first gas in the universe had almost no metals in that sense. It was overwhelmingly hydrogen and helium. The later enrichment of the cosmos came from generations of stars. The fact that the first nuclei were so simple shaped the first stars. Without heavier elements, the gas cooled differently. Cooling matters because gas clouds need to lose heat in order to collapse under gravity. Heavy elements and molecules can help gas cool efficiently, but the earliest clouds did not have them in abundance. This may have led the first stars to be very massive compared with many stars today. Those first stars then changed everything by forging heavier elements and scattering them into space when they died. But that future was still hidden inside the simple beginning. At the nuclear stage, the universe had made the raw material from which the first stars would one day form, but it had not yet made the conditions for stars to appear. There is a pleasing humility in the first nuclei. After all the immense physics of the beginning, after quarks and gluons, matter and antimatter, forces separating and particles surviving, the universe builds mostly hydrogen and helium. It is as though reality begins with the simplest possible vocabulary. 1 proton, 2 protons with neutrons, a little variation. Not a full dictionary yet, not poetry, not biology, just the first durable syllables of matter. Later the universe will become elaborate. It will make galaxies shaped like spirals and storms on giant planets, and nervous systems that can wonder why socks vanish in the laundry. But first, it makes hydrogen and helium. The nuclei themselves are held together by the strong nuclear force, though the details differ from the way quarks are bound inside protons and neutrons. Protons all carry positive electric charge, and positive charges repel each other through electromagnetism. So inside a nucleus with more than one proton, there is a tension. Electromagnetism pushes protons apart. The strong nuclear force, acting over very short distances, binds protons and neutrons together. Neutrons help because they contribute to the strong binding without adding electrical repulsion. This is why helium, with 2 protons and 2 neutrons, can be stable. The strong force wins at that tiny scale, holding the nucleus together. In the hot early universe, collisions between particles were frequent. A proton and neutron could meet and form deuterium. Deuterium could participate in further reactions, helium could form. But because the universe was filled with high-energy photons, any fragile nucleus faced the risk of being broken apart. The survival of deuterium marked a turning point. Once the radiation became gentle enough, in a relative sense, nuclear building could proceed. Gentle is a strange word here, because the conditions were still far beyond anything comfortable. But compared with the earlier universe, they were becoming less destructive. The cosmos was slowly changing from a place that smashed every structure into one that allowed the first structures to remain. This idea repeats throughout cosmic history. Structure forms when destructive processes weaken enough, or when binding processes become strong enough, or both. Quarks bind when the universe cools below a certain state. Nuclei survive when photons no longer constantly break them apart. Atoms form when electrons can remain attached to nuclei. Molecules form when atoms can bond without being torn apart. Stars form when gravity can gather gas into dense enough regions. Planets form when dust and gas can collect around young stars. Life forms when chemistry becomes complex and stable enough in suitable environments. Each step requires a balance between energy and stability. Too much disruption and nothing lasts. Too little interaction and nothing new forms. The universe builds by passing through these changing balances. For the first nuclei, the balance was brief but decisive. Once the early nuclear reactions ended, the relative amounts of hydrogen and helium were largely set for a long time. Stars would later process some hydrogen into helium and heavier elements, but the primordial mixture remained a foundation. Even now, most ordinary matter in the universe is still hydrogen. Helium is the second most abundant. The first nuclear choices of the cosmos still dominate the visible matter around us. They shape stars, galaxies, and cosmic evolution. The first nuclei were not a minor prelude. They were the first lasting composition of the universe. It is also worth remembering that ordinary matter, the matter made of protons, neutrons, and electrons, is only part of the total contents of the universe. Dark matter and dark energy play major roles in cosmic evolution, though they do not form atoms in the ordinary way. But the story of the first atom is the story of ordinary matter, the kind that interacts with light, forms chemistry, and eventually makes worlds. The first nuclei were the first stable centers of that ordinary atomic matter. They were small, simple, and almost unimaginably numerous. Spread through the expanding plasma, they waited through a long era before electrons could join them. After the first nuclei formed, the universe did not immediately become transparent. This is a common point of confusion. One might think that once hydrogen and helium nuclei existed, atoms must have appeared right away. But the electrons were still too energetic, and the radiation field was still too intense. Whenever an electron approached a nucleus and became bound, a photon could knock it loose again. For a long time, the universe remained ionized, meaning nuclei and electrons existed separately as charged particles. The first nuclei were like foundations laid in a storm, unable yet to support the full house because the weather had not calmed. The house, in this case, was the atom. So the universe entered a long waiting period. It had made the hearts of atoms within its first few minutes, but full atoms would not form in abundance until much later, after hundreds of thousands of years of expansion and cooling. That waiting period may seem strange. The first nuclei arrived quickly, and then atoms took far longer, but the delay makes sense. Binding electrons to nuclei requires much lower temperatures than binding protons and neutrons into nuclei. Nuclear forces are powerful at tiny distances. Electron binding is gentler and more easily disrupted by heat and radiation. The universe had to become far cooler before atoms could hold together. During this long stretch, the universe was filled with a plasma of nuclei, electrons, photons, and other particles. The nuclei were mostly hydrogen and helium. The photons continued to scatter off free electrons, keeping the universe opaque. Matter and radiation were tightly linked. Every region was still bathed in the after effects of the early fire. There were tiny density variations, and gravity was already beginning its patient work. But the strong coupling between matter and radiation prevented ordinary structures from forming quickly. The universe was becoming less extreme, but it was not yet calm. The first nuclei therefore mark both a success and a pause. They show that matter had become stable enough to form the cores of atoms. They show that the universe had cooled past another crucial threshold. But they also show that atom formation required more than nuclei. It required time, it required expansion, it required the radiation to lose enough energy that electrons could settle. The universe had built the hearts, but not the bodies. It had named the elements in the nuclear sense, but chemistry had not yet learned to speak. As we follow the story onward, we carry these nuclei with us. Lone protons will become ordinary hydrogen atoms when they capture electrons. Helium nuclei will become helium atoms when they capture 2 electrons. The tiny traces of other nuclei will become rare light atoms, but for now they remain bare, charged, and immersed in a glowing fog. There is still no clear light moving freely across space. There are still no molecules, no stars, no planets, no dust. Yet something essential has changed. The universe now contains the enduring cores of its first atoms, formed in a brief period when the temperature was just right for nuclear binding and not yet too low for reactions to occur. The next part of the story is not a sudden leap into chemistry, but a long, cooling hush as the universe waits for radiation to soften enough, for electrons to slow enough, and for the first true atoms to finally hold together. The first nuclei were now present, scattered through the young universe as bare centres of future atoms. There were lone protons, which would one day become the nuclei of hydrogen atoms. There were helium nuclei, each made from protons and neutrons bound tightly together. There were tiny traces of a few other light nuclei, so rare that they were more like footnotes in the early cosmic recipe than main ingredients. But even with these nuclei in place, the universe still could not make atoms in any lasting way. The hearts of atoms existed, but the atoms themselves were still waiting. The reason was simple in principle and extreme in practice. The universe was still too hot. When we say the universe was too hot for atoms, we do not mean too warm in the everyday sense, as if the early cosmos needed to sit by an open window for a while. We mean that the particles filling space still carried too much energy for electrons to remain bound to nuclei. A full atom needs a nucleus, and one or more electrons held around it. A hydrogen atom needs one proton and one electron. A helium atom needs a helium nucleus and 2 electrons. But in the young universe, electrons were not calmly settling into place. They were racing through a dense plasma, constantly interacting, constantly being knocked around by radiation and other charged particles. If an electron did attach to a nucleus, a high-energy particle of light could strike it and knock it free again almost at once. The result was a universe full of ingredients, but still unable to make stable atoms. It was rather like having flour, water, yeast and salt, but trying to bake bread inside a room where everything keeps exploding. The recipe may be promising, but the conditions are not yet friendly. This long interval after the first nuclei formed was a waiting period on a cosmic scale. The universe had already gone through rapid early changes. In its first moments, matter and antimatter had nearly erased each other, leaving behind a tiny excess of matter. Quarks had become confined inside protons and neutrons. Protons and neutrons had formed the first simple nuclei. All of that happened very early, while the universe was still incredibly hot and dense. Then the pace of visible change slowed, not because nothing was happening, but because the next major step required the universe to cool much more. Nuclei could form within the first few minutes, but stable atoms would not form in large numbers until much later. The universe had to expand for hundreds of thousands of years before electrons could stay attached to nuclei without being immediately stripped away again. During this long stretch, the universe was a plasma. That word is useful because it tells us that matter was ionized. The nuclei carried positive charge and the electrons carried negative charge, but they were not joined into neutral atoms. They moved separately through space. This meant the universe was filled with charged particles. Charged particles interact strongly with light, so photons could not travel freely for long distances. They were scattered again and again, mostly by free electrons. A photon might move a short distance, meet an electron, scatter in a new direction, move again, scatter again, and continue in this restless pattern. The universe was filled with light, but it was not transparent. This is one of the strangest parts of the story because it means the early universe was bright and opaque at the same time. In daily life, brightness usually helps us see. Turn on a lamp and the room becomes clearer. Open curtains and the morning makes furniture, books, and the questionable pile of clothes on a chair easier to identify. But brightness does not guarantee visibility. A thick fog can glow in sunlight while still hiding the road ahead. A cloud can be luminous, but impossible to see through. The early universe was similar in that broad sense. It was full of radiation, but that radiation could not stream freely across great distances. It was constantly scattered by the plasma. There were no stars to see, no galaxies, no clear background, no distant objects sending light across space. The whole universe was like a glowing fog with no outside observer, no horizon line, and no quiet dark gap between sources of light. This fog was not made of droplets or dust. It was a hot mixture of nuclei, electrons, photons, and other particles. The photons were the particles of light and radiation. They were everywhere, and there were far more photons than ordinary matter particles. Even after matter survived the Great Annihilation with antimatter, radiation remained overwhelmingly abundant. The universe was radiation-rich, and that radiation helped keep atoms from forming. Every time a nucleus and an electron tried to become a neutral atom, the surrounding sea of photons had many chances to break the bond. A stable atom requires the electron to lose enough energy and remain bound. In the early universe, the photons were still energetic enough to undo that attachment, so the universe stayed ionized. It may help to think of the nucleus as a person trying to hold an umbrella in a storm, except the storm is made of light, the umbrella is an electron, and the wind is so intense that any attempt to stay organized is immediately ruined. That image is not exact, of course, but it captures the frustration of the period. The universe had the pieces, but it could not keep them together. Stability was the missing ingredient. The expansion of space slowly provided it by cooling the radiation. As the universe expanded, the wavelengths of photons stretched, their energy decreased, the plasma became less hot, the collisions became less destructive. The universe gradually moved toward a state where electrons could finally settle around nuclei and stay there. This cooling took time because electron binding is much more delicate than nuclear binding. The strong nuclear force that holds protons and neutrons together inside nuclei works over extremely tiny distances and is very powerful. Once conditions allowed the first nuclei to survive, they could hold together against the surrounding radiation. But electrons are held to nuclei by the electromagnetic force in a much looser arrangement. Atoms are larger and more fragile than nuclei. They are not fragile in everyday life, because everyday temperatures are mild compared with the early universe. But in the early plasma, the energy was still far too high. A nucleus could survive where an atom could not. So the universe had to wait. During that waiting period, matter and radiation were tightly coupled. This means they behaved as an interacting mixture rather than as separate systems. Photons scattered from electrons, and electrons interacted with nuclei through electric forces. The radiation pressure resisted the tendency of matter to collapse under gravity. Tiny density differences existed, left over from much earlier times, and gravity was already beginning to amplify them very gently. Slightly denser regions pulled on surrounding material a little more strongly, but because radiation and matter were linked, the plasma also pushed back. The early universe was filled with waves of compression and rarefaction, a kind of pressure motion moving through the hot material. These were not sound waves in the way you hear a voice across a room, because there were no ears, no air, and no cozy room. But physically, they were pressure waves in the early plasma, and they later left measurable traces in the pattern of cosmic radiation and the distribution of matter. That detail matters because the long wait for atoms was not empty time. The universe was not simply sitting still, tapping its cosmic foot and checking a watch. It was expanding. It was cooling. Radiation and matter were interacting. Small density variations were being shaped by gravity and pressure. The future arrangement of galaxies was being gently prepared, even though galaxies themselves did not yet exist. The first stars were still far away, but the seeds of where matter would later gather were already present. The universe before atoms was not visually structured, but it was physically patterned. It carried faint differences that would later become very important. The opacity of the universe also means that we cannot see electromagnetic radiation from before atoms formed in the same direct way we see light from later times. Light before the universe became transparent was scattered so many times that it did not travel directly from a source to us. Once atoms formed, and the free electrons mostly disappeared into neutral atoms, photons could travel freely. The light released at that moment is the oldest light we can observe directly across the universe. Today, because space has expanded so much that ancient light has been stretched into microwave radiation, it fills the sky in every direction as a faint afterglow from the time the universe became transparent. This afterglow is one of the strongest pieces of evidence for the hot early universe. It is not light from the very first moment, but light from the moment the cosmic fog cleared. Before that clearing, there was no ordinary view. If someone imagines looking out into the early universe, they might picture a fiery sky. But there would be no looking in the usual sense. A viewpoint requires a place, a body or instrument, and light travelling from distant things to that place. In the plasma era, light could not carry distant images, it scattered too often. The universe did not yet have transparent space. It was not that there were objects hidden behind a curtain. The curtain was the state of the universe itself. Light and matter were still too entangled in their interactions for clear sight to exist. The term Dark Ages is sometimes used for a later period after atoms formed but before the first stars ignited. That phrase can be confusing here because before atoms the universe was not dark in the sense of lacking radiation. It was glowing and hot. The darkness of the later age came after the fog cleared, when the universe became transparent but had not yet formed stars to shine in visible light. For now, we are still before that. We are in the bright fog, the opaque plasma, the long time when atoms could not survive. The universe had light everywhere, but no clear path for light to travel. As the universe expanded, the temperature continued to fall. The important change was not simply that particles moved more slowly, though that was part of it. The radiation field itself softened. Photons became less able to knock electrons away from nuclei. At first, any neutral atoms that formed were quickly ionized again. Later, as the temperature dropped, the balance began to shift. More electrons could remain attached. The number of free electrons began to decrease. Once enough electrons became bound into neutral atoms, photons suddenly had far fewer charged particles to scatter from. The universe began to turn transparent. This transition is often called recombination, although the name is a bit misleading because electrons and nuclei were not recombining after having once been atoms before. They were combining into atoms for the first major time. The word remains because of historical usage, and science, like an old attic, sometimes keeps labels that are not quite perfect, but have been there too long to throw away. Before recombination could happen, the universe had to pass through a period when matter and radiation were cooling together but still coupled. The photons kept scattering, the electrons remained free, the nuclei remained bare. Hydrogen nuclei were mostly single protons. Helium nuclei carried greater positive charge and would later hold 2 electrons each. But the universe was still too energetic for these electron arrangements to settle. This meant there was still no chemistry. Chemistry depends on the behavior of electrons in atoms, especially the outer electrons. Without neutral atoms, there are no chemical bonds in the familiar sense. No molecules of hydrogen gas as we usually describe them. No water, no carbon compounds, no minerals, no dust. The universe had nuclei, but not chemistry. It had radiation, but not clear light. It had matter, but not materials. This is a useful distinction because matter is not automatically material in the everyday sense. We often use the word matter to mean stuff we can touch, but early matter was not touchable stuff. It was a charged plasma. Touch itself depends on electromagnetic interactions between atoms in your skin and atoms in an object. No atoms, no skin, no object, no touch. The early universe was matter without surfaces. It had particles but no solids, liquids, or ordinary gases. It had no textures. Nothing was rough, smooth, wet, dry, soft, or sharp. Those are later properties, produced by atoms and molecules arranged into structures. The universe at this stage was real, physical, and active, but it had not yet developed the ordinary qualities that make the world feel like a world. The wait for atoms was also a wait for the universe to become observable in a new way. Once photons could travel freely, they could preserve a snapshot of conditions at the time of release. That snapshot is not a photograph of objects, because there were still no stars or galaxies. It is a map of tiny temperature differences in the early radiation field. Those tiny differences correspond to slight variations in density and motion in the young universe. Today, scientists study this ancient radiation with extraordinary precision. It tells us the universe was once hot and dense. It tells us about the amount of ordinary matter, dark matter, and other cosmic ingredients. It tells us about the early ripples that later grew into galaxies. In a sense, the moment atoms formed gave the universe its first visible record. But during the waiting period itself, that record was still being written. The photons were still trapped in constant interactions. The plasma waves were still shaping the patterns that would later appear in the cosmic afterglow. Gravity, radiation pressure, and expansion were all involved. The universe was like an instrument being tuned before the first note could travel freely. That may sound a little too elegant for something so hot and dense, so let us bring it back to the kitchen. It was like soup simmering with the lid on. Plenty was happening inside, but you could not yet see clearly through it, and if you tried to stick your face over it too early, you would regret several decisions. The universe needed the lid to lift, and the lifting would happen when electrons finally joined nuclei. The reason free electrons are so important for opacity is that they scatter photons very efficiently. A free electron is an easy target for light compared with an electron bound inside a neutral atom under these conditions. Once electrons are bound, the universe becomes much less interactive with the background radiation. Photons can stream through space. That change did not require every single electron to become bound at once. It was a transition, but a rapid one compared with the long waiting period before it. The fog thinned. The distance a photon could travel before scattering grew enormously. Space became transparent. Still, even as the universe approached that transition, it did not happen because atoms were somehow eager to form. Nature does not work by eagerness. It happened because the rates changed. The rate at which electrons attached to nuclei began to beat the rate at which photons knocked them loose. As temperature fell, ionization became less common. Neutral atoms became more common. At a certain point, the balance shifted dramatically. Most ordinary matter became neutral hydrogen and helium. The charged plasma became a neutral gas. Light decoupled from matter and travelled freely. The first full atoms finally appeared in abundance. Before that, however, there is value in sitting a little longer with the long wait itself. Hundreds of thousands of years may sound enormous from a human perspective. Civilizations rise and fall in far less time. Mountains can be worn down noticeably over longer spans, but a few 100,000 years is still a serious amount of time if you're waiting for your tea to cool. Yet compared with the age of the universe today, it was early. The universe was still young, but no longer in its first frantic moments. It had moved from rapid particle transformations to slower cosmic cooling. This shift from seconds and minutes to hundreds of thousands of years is part of the changing rhythm of cosmic history. The early universe did many foundational things quickly, then waited for expansion to make the next stage possible. This long wait also reminds us that atoms are not inevitable at every temperature. We live in a cool universe, so atoms seem natural. They are so common that it takes effort to imagine their absence. But atoms are conditional. They require a universe with the right particles, the right forces, and the right temperature. Too hot, and atoms are stripped apart. Too violent, and electrons cannot stay bound. In stars today, much of the matter is plasma for this very reason. Atoms can be ionized by extreme heat. The early universe was like that everywhere. What we now find inside stars was once the general condition of the cosmos. The whole observable universe was a kind of hot plasma environment before it cooled into neutrality. There is a quiet reversal here. Today, stars are hot islands in a mostly cold universe. Long ago, before atoms, the universe as a whole was hot and opaque. Later, after atoms formed, space became transparent and eventually dark until stars ignited. Then light returned in concentrated sources. The universe moved from everywhere glowing but nowhere transparent, to transparent and dark, to a cosmos lit by stars and galaxies. The first atom sits at the center of that transformation. It is not just the beginning of chemistry. It is part of the reason light could begin to cross the universe without being constantly interrupted. The first atoms also changed the relationship between ordinary matter and radiation. Before atoms, radiation pushed strongly on matter through free electrons. After atoms formed, radiation moved more independently. Matter could then begin to fall more freely under gravity into the slightly denser regions seeded earlier. This would eventually help form the first large structures. The transition to neutral atoms therefore opened the way not only for clear light, but for gravitational growth. Matter could gather without being as tightly dragged along by radiation. The universe became more ready for clouds, and clouds would one day become stars. But we are still just before that release. The nuclei are waiting in the plasma. Electrons move freely around them. Photons scatter constantly. The temperature continues its steady decline as space expands. No star has yet turned on. No planet has formed. No molecule drifts in a cold cloud. The first atoms are close in the cosmic sense, but the universe has not crossed the threshold. It remains too hot for electrons to remain attached in large numbers. The fog still holds. One can think of this period as a long preparation for two arrivals at once: the arrival of atoms and the arrival of freely travelling light. The two are connected. When atoms form, free electrons disappear into neutral structures. When free electrons disappear, photons stop scattering so often. When photons stop scattering, the universe becomes transparent, so the first atom is also tied to the first clear view. It is as though matter had to become neutral before light could become a traveller. Until then, light was present but trapped in conversation with the plasma, interrupted at every turn, unable to carry a message across the growing universe. The next great moment comes when the cooling finally reaches the point where hydrogen and helium atoms can hold together. Lone protons capture electrons and become hydrogen. Helium nuclei capture electrons and become helium atoms. The fog thins. Photons stream away, carrying with them the ancient pattern of the young universe. Chemistry is still very simple, almost entirely hydrogen and helium, with only tiny traces of anything else. There are still no stars, no heavy elements, no planets. But for the first time, the universe contains neutral atoms, and that changes the behaviour of matter and light everywhere. The long wait is nearly over, and the simplest atom, modest hydrogen, is about to become the first familiar piece of the material world. The long wait finally reached the point where the universe could do something it had been preparing to do for hundreds of thousands of years. It could let an electron stay. That sounds almost too small after everything that came before. We have moved through energy becoming matter, matter surviving antimatter, quarks binding into protons and neutrons neutrons forming the first nuclei. We have spent time inside a universe too hot for atoms, too bright to see through, too full of charged particles for light to travel freely. And now the great turning point comes down to something wonderfully modest. A single electron, no longer struck away immediately, can settle into the influence of a single proton. When that happens, the simplest atom appears: hydrogen. Hydrogen is not dramatic in appearance. It does not sparkle like gold, glow like neon, or smell like rain on warm stone. In its simplest form, it is just one proton and one electron held together by electromagnetic attraction. That is all. One positive centre, one negative companion, and a small stable structure that can last. But this quiet little arrangement changed the universe. Before hydrogen atoms formed in great numbers, the cosmos was an ionized plasma, a glowing fog of nuclei, electrons and radiation. After hydrogen atoms formed, much of ordinary matter became neutral. Light could finally move through space without being scattered at every moment. Matter began to behave less like a charged storm and more like a gas that gravity could later gather into clouds. The first hydrogen atom was not just a tiny object. It was a doorway into a new kind of universe. To appreciate why this mattered so much, it helps to remember what had been missing. The universe already had hydrogen nuclei, because a lone proton is the nucleus of hydrogen. Those protons had existed since the earlier stages when quarks became bound into stable particles. But a proton alone is not a complete atom. It carries positive electric charge. It is exposed, bare, and strongly interactive with the surrounding plasma. A full hydrogen atom forms only when that proton captures an electron and becomes electrically neutral overall. Neutrality is the key. It may not sound exciting because in daily life, neutral often means undecided, quiet, or possibly the colour of a very serious sofa. But in the early universe, neutrality was revolutionary. Charged particles scatter light strongly. Neutral atoms do so far less in the conditions of the early cosmos. When matter became neutral, light gained its freedom. The formation of hydrogen atoms happened as the universe cooled. Not all at once in a single cosmic tick, and not in one special location, but throughout space as the temperature dropped below the level where energetic radiation could keep tearing electrons away. For a long time, every attempt at forming a hydrogen atom was undone. A proton and electron could meet, but a photon would strike and ionize the atom again. The bond could not survive. The universe was like a room where every candle is blown out the instant it is lit, except the room is everywhere and the candles are atoms. Eventually the radiation softened enough that more atoms formed than were destroyed. The balance shifted. Free electrons began disappearing into neutral atoms. The fog began to clear. This event is often called recombination, although that name can give the wrong impression. It sounds as if electrons and nuclei had been combined before and were now coming back together after a separation. In the early universe, this was really the first major combination of electrons with nuclei into stable atoms. But historical names have a way of lingering, a bit like old labels on boxes in a cupboard. The important point is that the plasma became a neutral gas. Hydrogen became the dominant atom. Helium atoms formed as helium nuclei captured electrons as well. There were tiny traces of other light atoms, but the universe was overwhelmingly hydrogen and helium. No oxygen, no carbon, no iron, no silicon, no calcium. None of the elements that later make rocks, bones, oceans, or the spoon that somehow always disappears just when the soup is ready. Hydrogen was the beginning of atomic familiarity, because it gave matter a form we can recognize as part of the world we know. It was still not familiar in the sense of planets, air, water, or anything solid, but it was familiar in the deeper sense that atoms had arrived. Matter was no longer mainly a charged plasma. It could now exist as neutral atoms, the basic units from which chemistry would eventually grow. Hydrogen itself is chemically simple, but it is not chemically meaningless. Much later, hydrogen atoms would join into hydrogen molecules, gather into clouds, feed stars, and take part in the chemistry of water, organic molecules, and living cells. At the moment of first atom formation, all of that was still far ahead. But the door had opened. The first hydrogen atoms also helped create the oldest light we can still observe directly. Before neutral atoms formed, photons were constantly scattering from free electrons. They could not travel far in straight paths. Once electrons became bound inside atoms, there were far fewer free electrons to scatter the photons. Suddenly, by cosmic standards, light could stream across space. The photons that were released at that time have been travelling ever since, stretched by the expansion of the universe into microwave radiation. Today they form a faint glow in every direction, the afterimage of the time when the universe became transparent. This glow is not light from the first instant of existence. It is light from the moment the fog cleared. In a very real sense, the first atoms made the universe visible. This is a beautiful connection. An atom is usually thought of as matter, something solid or chemical or material. Light is usually thought of as something separate, something that shines on matter or passes through space. But in the early universe, the formation of atoms changed what light could do. Matter had to become neutral before light could travel freely. The first hydrogen atoms helped release the ancient radiation that now gives scientists one of their best windows into the young cosmos. If the universe had remained ionized, that light would not have streamed away in the same clean way. The arrival of atoms was also the arrival of transparency. Of course, there was no one there to see it. No eyes, no telescopes, no planets with observatories, no tired astronomer adjusting a chair at 3 a.m. The universe became transparent long before there were observers, yet it left a record that observers could later read. The ancient light carries tiny variations in temperature and density, faint patterns from the early plasma. Those patterns are like the fingerprints of the young universe. They tell us about its contents, its geometry, its expansion, and the small seeds that later grew into galaxies. The first atoms did not create those patterns, but they allowed the light carrying them to escape. They turned a trapped glow into a travelling message. Hydrogen itself is wonderfully simple, and that simplicity is why it came first in such abundance. A single proton was already available in huge numbers, left over from the earliest particle history. Electrons were also present, balancing the positive charge of matter overall. Once conditions cooled enough, the electron and proton could form a stable atom. Helium also formed atoms, but it required a helium nucleus capturing 2 electrons, and helium nuclei were less abundant than protons. Hydrogen therefore dominated. It remains the most abundant element in the universe today. The stars, the vast gas clouds between galaxies, and much of the visible matter of the cosmos are still built mainly from hydrogen. The first atom was not only first, it stayed important. The word familiar in this stage should be treated carefully. A single hydrogen atom is not familiar in the way a chair is familiar. You cannot see one with your eyes. You do not experience it directly, but atoms are the basis of all ordinary materials, and hydrogen is the simplest of them. Once hydrogen exists, the universe has crossed into the kind of matter that can later form chemistry. It now contains stable units, with electrons arranged around nuclei. Those electrons will eventually determine how atoms interact, how they bond, how they absorb and emit light, and how matter becomes rich in behaviour. Before atoms, there is nuclear physics and plasma. After atoms, chemistry becomes possible, though not immediately complex chemistry. It is like the first quiet word in a language that will one day produce libraries. At the time hydrogen formed, the universe was still extremely simple. There were no stars yet. That is important because stars are often associated with light, and one might imagine that once the universe became transparent, it was filled with starlight. But the first stars had not formed. After the ancient radiation streamed free, the universe entered a period that was transparent but dark in visible light. The gas was mostly hydrogen and helium, spread through expanding space, with small density variations left from earlier times. No stars burned within it yet. The universe had become see-through, but there was not much to see. The old glow faded into longer wavelengths as space expanded, and the first starlight still waited in the future. This later dark period was not empty or still. Gravity was working. The tiny density variations from the early universe meant that some regions contained slightly more matter than others. Once matter was neutral and less tightly coupled to radiation, it could begin falling more freely under gravity. Slightly denser regions grew denser over time. Gas began gathering into broad cosmic structures. Dark matter, which does not interact with light the way ordinary matter does, had already been helping shape gravitational wells. Ordinary hydrogen and helium gas could fall into those wells. Slowly, over immense stretches of time, these gatherings would become the first star-forming clouds. The first atoms made this later collapse easier by freeing matter from the constant push and drag of radiation. Hydrogen atoms also introduced a new way for matter and light to interact. Atoms can absorb and emit light at particular energies, leaving spectral fingerprints. Much later, when stars and gas clouds formed, these fingerprints would allow astronomers to identify what the universe is made of. Every element has characteristic patterns. Hydrogen has its own, simple but powerful. It would become one of the most important tools in astronomy. By studying hydrogen light, scientists can map gas in galaxies, measure motion, study star formation, and trace the large-scale structure of the cosmos. This simplest atom became one of the universe's most useful signatures. Hydrogen is quiet, but it is not shy when given the right conditions. The early hydrogen atoms were not arranged into molecules immediately in large amounts. Forming molecules requires atoms to meet, interact, and shed energy in ways that allow a bond to remain. The universe was still diffuse and expanding. Over time, small amounts of molecular hydrogen could form, and this became very important for the first star formation because molecular hydrogen can help gas cool. Cooling allows gas clouds to collapse more efficiently. But in the main moment we're considering, the crucial transition was from free protons and electrons to neutral hydrogen atoms. Molecules, stars, and heavier chemistry would come later, carried forward by gravity and time. There is something almost gentle about an electron settling around a proton after such a violent early history. The universe began in conditions where stability was difficult. Particles formed and vanished. Matter and antimatter destroyed each other. Quarks were bound by the strong force. Nuclei survived only after radiation became less destructive. Then came a long wait while electrons remained free. At last, the temperature dropped enough. The electron could stay. The proton could hold it. Neutral hydrogen could exist. It is not peaceful in a sentimental sense, because the universe was still hot by human standards and filled with radiation, but compared with the earlier stages, it was a calming, a settling, a shift from constant scattering toward transparency. The first hydrogen atom did not form alone in a meaningful practical sense. Conditions changed across the universe, and atom formation happened everywhere the plasma cooled enough. There may have been a first individual neutral hydrogen atom somewhere in the statistical blur of cosmic history, but science does not identify it like a person cutting a ribbon at an opening ceremony. What matters is the transition as a whole. The universe went from almost completely ionized to mostly neutral. Hydrogen atoms became abundant. Helium atoms formed too. The fog cleared. The first atom is less a single object we can point to, and more a threshold crossed throughout the cosmos. This threshold had a temperature, a density, and a time in cosmic history. But since you asked for everything verbally and without formulas, we can say it simply. It happened when the universe had cooled enough, after hundreds of thousands of years, for electrons to remain bound to nuclei. Before that, the radiation was too energetic. After that, stable atoms could survive. This is enough for the story. The exact numerical details are useful in textbooks and research papers, but the main idea is that cooling made neutrality possible, and neutrality made transparency possible. From a human perspective, hydrogen may seem humble because we rarely notice it directly. On Earth, hydrogen is often bound inside other substances, especially water and organic compounds. Free hydrogen gas is light and escapes easily from small rocky planets unless conditions keep it contained. Yet across the universe, hydrogen is everywhere. It is the main ingredient of stars. It is the fuel that powers most of their lives. It forms immense clouds and galaxies. It fills intergalactic space in thin traces. It is the simple atom from which cosmic complexity begins. The hydrogen in your body is ancient in a special way. Many of your hydrogen atoms may trace their nuclei back to the early universe itself. The oxygen in your water was made later in stars, but the hydrogen likely carries the older signature of the first cosmic matter. That thought brings the story very close. Every sip of water contains hydrogen, whose central protons may have formed in the first moments after quarks became confined. Those protons later became part of hydrogen atoms when electrons joined them. They travelled through cosmic history, through gas clouds, through stars and planetary systems, into Earth, into oceans, into living things. The simplest atom connects your body to the earliest stages of matter. This does not mean the exact electron in a hydrogen atom has stayed with the same proton forever. Electrons can be exchanged in chemistry, and atoms can be ionized and recombined in many environments. But the protons themselves are extraordinarily old. The heart of hydrogen is among the oldest durable pieces of ordinary matter in existence. Hydrogen also teaches us that simplicity can be powerful. With one proton and one electron, it might seem almost too plain to matter. But the universe uses hydrogen as fuel, structure, and signal. Hydrogen clouds collapse into stars. Stars fuse hydrogen into helium and release light. That light warms planets and drives chemistry. Later generations of stars build heavier elements from the products of earlier ones. Complex atoms depend on stellar histories that begin with hydrogen. Without hydrogen, the universe would not have the same path towards stars, galaxies, planets, or life. The first atom was simple because the universe needed to begin somewhere stable. The formation of helium atoms alongside hydrogen also mattered, though helium is chemically quiet. Helium atoms are stable and do not easily bond with other atoms. They are like polite guests who attend the cosmic gathering but decline most invitations to dance. Hydrogen, by contrast, can participate in chemistry more actively later on. But in the early universe, both hydrogen and helium contributed to the neutral gas. Both reduced the number of free charge particles. Both helped the universe become transparent. The mixture of hydrogen and helium would shape the first star-forming clouds. Helium added mass and influenced the behavior of the gas, even if hydrogen remained the main actor. Once atoms formed, the universe had matter that could cool in new ways. Neutral atoms do not respond to radiation pressure as strongly as charged particles in a plasma. They can fall into gravitational wells more effectively. Over time, the smallest early density differences became more pronounced. Regions with slightly more matter attracted still more matter. Gas flowed inward. Dark matter structures helped guide the process. The first cosmic web began to emerge, though still without stars for a while. Hydrogen was now the material gravity could gather. The first atom was not just a particle. It was the beginning of gas clouds, and gas clouds were the beginning of stars. The word gas here is closer to what we can imagine, though it was still nothing like air in a room. There was no oxygen, no nitrogen, no pressure you could breathe, no atmosphere surrounding a planet. It was a thin cosmic gas made mostly of hydrogen and helium, spread across enormous distances. But compared with plasma, it was a more familiar state of matter. Neutral atoms moving freely through space. That is something we can connect to gases in laboratories, nebulae, and the spaces between stars. The universe had taken a step toward the ordinary categories we use today. This is why hydrogen marks the moment matter became familiar. Not fully familiar. There were still no rocks, no oceans, no molecules of life, no planets, no stars. But matter had become atomic. It had entered the family of forms that our everyday world is built from. If you could strip away all later complexity and ask when the universe first had the basic kind of stuff that chemistry would later use, this is the moment. Hydrogen atoms, helium atoms, neutral gas, transparent space. The universe was still young, but it had learned how to hold electrons, and because light could now travel, the universe had also created a boundary in what we can directly observe. When we look far enough into space, we look back in time. But with ordinary light, we can only look back to the time when the universe became transparent. Before that, the plasma blocks a direct view. The first atoms therefore form a kind of visible horizon. Beyond it, we use other evidence and theory, but the ancient light itself begins there. Hydrogen did not merely become matter, it helped draw the oldest observable picture of the cosmos. As space continued expanding, the released radiation cooled and stretched. The neutral hydrogen and helium gas also cooled. The universe became darker in visible light. The first atoms drifted in growing regions of slightly different density. Gravity continued its slow gathering. There was no sudden burst of stars immediately after atoms formed. The cosmos had patience still to practice. But the conditions had changed permanently. The charged fog was gone. Matter could clump more freely. Light could cross vast distances. The simple atom had remade the behavior of the whole universe. From this point onward, the story begins to move from the birth of atoms toward the birth of structures. Hydrogen and helium are present, but they are not enough by themselves to make planets or life. They must gather. They must collapse into the first stars. Those stars must ignite. Inside them, hydrogen will become helium, and later generations of stars will create heavier elements. The first atom is therefore not the end of the story of matter, but the beginning of matter becoming useful to cosmic construction. Hydrogen gives the universe fuel, gravity gives it direction, time gives it room to change. So we leave the moment of first hydrogen not as a completed universe, but as a universe newly transparent and newly atomic. It is mostly simple gas and ancient light, with small variations spread through space. It has no chemistry beyond the very simplest beginnings, no heavy elements, no shining stars. Yet it now contains the basic material from which the next transformations can proceed. A proton has held an electron. Light has slipped free. The fog has thinned. Matter has become, for the first time, recognizably atomic. And in the quiet darkness that follows, hydrogen begins its long journey toward clouds, stars, and the first acts of cosmic chemistry. After the first hydrogen and helium atoms formed, the universe entered a quieter but not empty stretch of its history. The bright fog had cleared. Light could travel. Matter was no longer tied so tightly to radiation. The cosmos had become transparent, but it had not yet become bright in the familiar way. There were no stars shining in the distance, no galaxies with spiral arms, no glowing nebulae, no planets reflecting sunlight, and no night sky full of points. The universe had atoms, but it did not yet have lamps. It was mostly a vast, cooling mixture of hydrogen and helium, spread thinly through expanding space, with small unevennesses in density that would one day matter very much. If the first atom was the moment matter became familiar, this next period was the time when familiar matter began slowly preparing to gather. It is tempting to imagine that once atoms existed, stars would quickly follow. After all, hydrogen is the fuel of stars, and now the universe had plenty of it. But the cosmos still had a great deal of work to do before the first star could ignite. A star is not just a pile of hydrogen, it is a huge, dense, self-gravitating sphere, hot enough in its core for nuclear fusion to begin. To make one, gas has to collect. It has to lose energy. It has to collapse under gravity. It has to grow denser and hotter in just the right way. And in the early universe, that was not easy. The atoms were simple. The gas was thin. Heavy elements did not yet exist to help the gas cool. Dust did not exist. Planets did not exist. There were no rocky grains, no carbon compounds, no oxygen molecules, no metals in the astronomer's sense, and certainly no convenient cosmic thermostat mounted on the wall. The universe after the first atoms was therefore simple, but not finished. It had mostly hydrogen atoms, some helium atoms, and traces of a few other light atoms. Hydrogen was the main ingredient. Helium was important but chemically shy. It rarely forms bonds because its electrons are arranged in a very stable way. Hydrogen, by contrast, can form molecules, and this became crucial. The first chemistry was not rich chemistry. It was not the chemistry of water, rock, sugar, leaf, smoke, or the slightly mysterious smell of a cupboard that has not been opened in years. It was a very limited chemistry, mostly concerned with whether hydrogen atoms could join together and form molecules made of two hydrogen atoms. Yet that modest little molecule helped prepare the universe for stars. To understand why, we need to think about cooling. gas cannot collapse efficiently into a star unless it can get rid of some of its heat. When a gas cloud contracts under gravity, it tends to heat up. The particles move faster as gravitational energy turns into thermal motion. If the gas cannot radiate that energy away, pressure builds and resists further collapse. Cooling allows the gas to keep falling inward, becoming denser and denser until the center becomes hot enough for fusion. In the modern universe, gas clouds can cool in many ways. Atoms and molecules of heavier elements can emit radiation. Dust grains can absorb and release energy. Carbon, oxygen, and other elements provide many channels for cooling. But the first gas had almost none of that. It was mostly hydrogen and helium, and those atoms alone were not very efficient at shedding heat under the conditions of the early star-forming clouds. This is where molecular hydrogen becomes important. A molecule made of two hydrogen atoms can emit energy in ways that a lone hydrogen atom cannot do as easily in those early conditions. It is not a perfect coolant, and it is not nearly as efficient as the cooling available in later, more chemically enriched gas. But in the first universe, it was one of the few tools available. Molecular hydrogen allowed some gas clouds to lose enough heat to collapse further under gravity. It was a small chemical step with enormous consequences. Before there were stars, chemistry helped make stars possible. Not complex chemistry, not the chemistry of life, but the simplest chemistry that mattered at the right moment. The formation of molecular hydrogen was not straightforward. In the young neutral universe, most hydrogen atoms remain separate. For two hydrogen atoms to form a stable molecule, they had to find a way to carry away excess energy. If they simply collided, they might not remain bound. In today's interstellar clouds, dust grains help hydrogen atoms meet and combine. Atoms stick briefly to the surfaces of tiny grains, find partners, and leave as molecules. It is a rather charming process when described gently, like matchmaking on microscopic specks of cosmic dust. But the first universe had no dust, because dust requires heavier elements, and heavier elements require stars. So the first molecular hydrogen had to form through slower, less efficient gas phase reactions, involving rare charged particles and free electrons left over from the time of recombination. That leftover fraction of charged particles mattered. Even after the universe became mostly neutral, not every electron found a nucleus immediately. A small number of free electrons and ions remained. These charged particles helped catalyze the formation of molecular hydrogen. They allowed temporary combinations to form, which then reacted with hydrogen atoms to produce stable molecules. The details are technical, but the main idea is simple. The first chemistry needed a little help from the leftovers of the plasma era. The universe had become neutral, but a small trace of ionization helped create the molecules that would allow gas to cool. It is another example of the cosmos using what remains from one stage to prepare the next, like leftovers becoming soup the following day, only with less celery and more gravity. While this chemistry was beginning, gravity was working on larger scales. The early universe was not perfectly smooth. It had tiny density variations, small regions where matter was slightly more concentrated than elsewhere. Dark matter played a major role here. Although dark matter does not form atoms, emit light, or participate in ordinary chemistry, it has gravity. It began clumping earlier and more freely than ordinary matter, because it was not pushed around by radiation in the same way. These dark matter concentrations created gravitational wells. Ordinary hydrogen and helium gas could fall into them once it was neutral enough to move more independently from radiation. In this way, dark matter helped gather the first atomic gas into the places where stars could eventually form. This is a strange partnership. The first stars were made of ordinary matter, mostly hydrogen and helium, but their birth was guided by dark matter. Dark matter provided the invisible scaffolding. Ordinary gas fell into it. Molecular hydrogen helped the gas cool. Gravity pulled inward. Pressure pushed outward. The whole process was slow at first, then increasingly intense as collapse proceeded. The The universe, once almost evenly filled with simple atoms, began to develop structure. Slightly denser regions became more dense. Clouds formed within larger halos of dark matter. The first star-forming regions began to take shape. There were still no heavy elements in those clouds. This made the first stars different from stars born today. Modern stars usually form in gas that contains at least some heavier elements, and dust from earlier generations of stars. This extra material helps the gas cool and fragment into many smaller clumps. That is why star-forming regions today can produce stars of many masses, including small, long-lived stars. The first gas, with its limited cooling, may have had a harder time breaking into small pieces. Many scientists think the first stars were often very massive, much more massive than the Sun. They may have burned hot, bright and short lives. They were not gentle little stars settling in for billions of years with a cup of tea and a reliable routine. They were more like enormous cosmic furnaces that arrived late to the dark universe and then made quite an entrance. Before they ignited, however, their gas clouds had to collapse. Imagine a region of hydrogen and helium gas falling inward under gravity. As it contracts, the center grows denser. Molecular hydrogen radiates away some energy, allowing the collapse to continue. The gas does not fall in perfectly smoothly. It swirls, fragments, shocks, and heats. Parts of it may form dense knots. A central protostar begins to develop, not yet a true star powered by fusion, but a growing object heated by gravitational collapse. More gas falls onto it. Its mass increases. The pressure and temperature at its center rise. The forming star becomes brighter as it releases energy from contraction. Still, the decisive moment has not yet happened. A true star begins when the core becomes hot and dense enough for hydrogen nuclei to fuse into helium. Fusion is the process that powers stars. In a star's core, hydrogen nuclei are pressed together under extreme temperature and pressure. When fusion begins, energy is released. This energy pushes outward and can balance the inward pull of gravity. A star becomes stable, at least for a while, because gravity and internal pressure find a working balance. In the first stars, this ignition marked the end of the cosmic dark ages in a practical sense. Light from the first stars began to shine through the universe. The simple atoms that had once made the universe transparent were now gathering into objects that produced new light. Hydrogen, the first atom, had become fuel. This was a major turning point. The universe before stars had atoms but little visible light from objects. The ancient afterglow from recombination had been stretched into longer wavelengths as space expanded. The cosmos was transparent but dark. Then the first stars turned on, and light returned in a new form. Not the trapped light of the hot plasma, and not only the fading afterglow of the early universe, but starlight. Local, intense, structured light from gravitationally bound furnaces. The first stars began changing their surroundings immediately. Their ultraviolet radiation heated and ionized nearby gas. Their winds and radiation pushed on the material around them. They began carving the early universe into regions of ionized and neutral gas. The first stars also began the process of making heavier elements. This is where the story of atoms expands beyond hydrogen and helium. In their cores, stars fuse lighter nuclei into heavier ones. Massive stars can build elements such as carbon, oxygen, neon, magnesium, silicon, and iron through successive stages of nuclear burning. When massive stars die, they can explode and scatter these newly made elements into space. Some explosions also create even heavier elements through rapid nuclear processes. The details vary depending on the star and the kind of death it undergoes, but the broad result is clear. Stars take the simple matter of the early universe and enrich it. They turn a hydrogen and helium cosmos into a universe capable of chemistry in the richer sense. The first generation of stars was therefore not only a source of light, it was the first major source of chemical complexity. Before them, the universe could make only a few light nuclei. After them, heavier elements began to spread. Those elements would later cool gas more efficiently, allowing new generations of stars to form differently. They would form dust grains. They would become the ingredients of rocky planets. Carbon would become part of organic molecules. Oxygen would become part of water and minerals. Iron would settle into planetary cores and blood cells. Calcium would become bone. Phosphorus would become part of the chemistry of life. None of that existed in the first neutral gas. It had to be made by stars. This gives the first stars a kind of double role. They were born from the simplest chemistry, and then they created the conditions for complex chemistry. Molecular hydrogen helped the first gas clouds cool enough to form stars. Those stars then made heavier elements, and those heavier elements later allowed gas clouds to cool better, fragment more finely, and form more varied stars and planetary systems. The universe began with a very limited chemical toolkit. Used it to make the first furnaces, and then the furnaces made a better toolkit. This is not planning, but it has the satisfying feel of a process bootstrapping itself, one stage enabling the next with whatever crude tools it has available, like fixing a shelf with the wrong screwdriver, succeeding just enough to later build a proper workshop. The first stars likely lived fast if they were very massive. Massive stars burn through their fuel quickly because their cores are hotter, and their fusion rates are intense. A star many times heavier than the Sun may live only a few million years, which sounds long until you compare it with the Sun's much longer lifetime. In cosmic history, a few million years is a short bright flare. When these first stars died, they may have exploded with tremendous force, sending heavy elements outward into surrounding gas. Their deaths were destructive, but also creative. They broke apart the simple purity of the early universe and seeded it with new atomic possibilities. Every later rocky world depends on such enrichment. Without the deaths of stars, the universe would have remained mostly hydrogen and helium, with little chance of making planets like Earth. The gas enriched by the first stars could form later stars. These later stars contained small amounts of heavier elements mixed into their hydrogen and helium. Even a tiny amount of heavy material changed how the gas cooled. It made star formation more efficient and allowed smaller stars to form more easily. Some of those smaller stars could live for billions of years, providing stable light over long times. Around later stars, disks of gas and dust could form. Dust grains could stick together, growing into larger grains, pebbles, rocks, planetesimals, and eventually planets. The first chemistry did not directly make planets, but it set the chain in motion. Hydrogen formed atoms. Molecular hydrogen helped make stars. Stars made heavy elements. Heavy elements made dust and planets possible. There is a lovely continuity in this sequence, though we should keep our feet on the ground. It was not smooth or tidy everywhere. The early universe was patchy. Some regions formed stars earlier than others. Radiation from the first stars affected nearby gas and changed future star formation. Explosions stirred and heated material. Dark matter halos merged into larger structures. Gas flowed along filaments. Galaxies assembled gradually, through many collapses, mergers, bursts of star formation, and quiet intervals. The universe did not go from hydrogen to a neat spiral galaxy in one clean step. It built structure through many overlapping processes, most of them messy enough to comfort anyone whose desk is not perfectly organized. As more stars formed, their light began changing the state of the gas between galaxies. The first stars and early galaxies produced energetic radiation that could ionize hydrogen again, stripping electrons from atoms across large regions of space. This later transformation is known as reionization. It did not return the universe to the dense glowing fog of the earliest plasma, because space was much more expanded and thin by then. But it did change the intergalactic gas. The first atoms had made the universe neutral and transparent. The first stars then began ionizing much of that gas again, while the universe remained transparent because the density was far lower than before. This stage marks another major shift in cosmic history, as starlight and galaxy formation began reshaping the wider cosmos. The relationship between atoms and light therefore continued to evolve. In the beginning, charged particles trapped light. Then neutral atoms released it. Later, stars formed from neutral gas and produced new light. That light ionized gas again. Each stage changed how matter and radiation interacted. The first atom did not end the story of light. It began a new relationship between matter and light, one that allowed observation, structure, and eventually the rich astronomical universe we study today. For the topic of the first atom, the important point is that simple atoms were not an endpoint. Hydrogen and helium were stable, but stability alone does not make complexity. The universe needed gravity to gather them, and chemistry to help them cool. The first molecules, especially molecular hydrogen, acted as cooling agents in the earliest collapsing clouds. This was the first small step from atoms toward astrophysical structure. It was not enough to create life, planets, or complex molecules yet, but it was enough to help create the first stars. Once stars existed, the universe had a way to make the heavier atoms that simple early conditions could not produce. This is why hydrogen is both an atom and a beginning. It is matter's simplest stable form, and it is also the fuel from which stars are born. The first hydrogen atom drifted in a dark, transparent universe, but they were not idle. They were subject to gravity. They gathered into regions shaped by dark matter. Some of them formed molecules, some clouds cooled, some collapsed, some ignited. Through this sequence, the universe moved from atomic matter to luminous structure. It began with hydrogen atoms and ended much later with galaxies full of stars. Not ended in the final sense, of course, because the story keeps branching into heavier elements, planets, chemistry, and eventually ourselves. But the path from simple atoms to stars is one of the main bridges. It is also one of the reasons the phrase came from nothing needs care. The first atom did not come from an empty void in one instant. It came from a chain of physical stages, and once it came, it did not immediately make everything else. It prepared the universe for further stages. Hydrogen and helium were simple, but they provided the material from which gravity could begin building. The first chemistry was sparse, but it allowed cooling. The first stars were made from that cooled gas, and those stars produced the elements that later made richer chemistry possible. The universe became complex by using simple things repeatedly in new settings. Consider a hydrogen atom drifting in the young universe after recombination. For a long time, it may simply move with the expanding gas. It may pass through regions slightly denser or thinner than average. If it lies within a growing gravitational well, it may slowly fall inward with other atoms. It may join a molecule. It may become part of a collapsing cloud. It may be drawn into the forming body of a first star. In the star's core, its proton may eventually fuse with others, becoming part of helium and releasing energy as starlight. That starlight may travel outward and help heat or ionize surrounding gas. If the star later dies violently, material around it may be enriched with heavier atoms. The original hydrogen may be transformed, but the process it participates in changes the universe around it. One simple atom becomes part of a story much larger than itself. In that sense, the first atoms prepared the cosmos not by being complicated, but by being available. They were stable enough to gather. They interacted through gravity. They could form limited molecules. They could become fuel. They could be processed inside stars. They gave the universe something to work with after the plasma cleared. A universe with no atoms could not form ordinary stars. A universe with atoms but no cooling chemistry would struggle to collapse gas into the first luminous objects. A universe with hydrogen, helium, dark matter structure, and a little molecular hydrogen had a path forward. The first chemistry may sound small, and in terms of variety it was small. But science often finds that small steps at the right time matter greatly. A trace of free electrons helps form molecular hydrogen. Molecular hydrogen cools gas. Cooling gas collapses. Collapse makes stars. Stars make heavy elements. Heavy elements make dust, planets, and complex chemistry. The chain is long, but the early links are essential. Remove one, and the later universe changes dramatically. It is rather like trying to make a long bedtime story while skipping the first page. You might still have words, but the whole thing begins to wobble. By the time the first stars began to shine, the universe had moved far from the featureless plasma of its youth. It now had neutral atoms, molecules in small amounts, dark matter halos, collapsing gas clouds, and the first sources of starlight. The first star-forming regions were likely embedded in larger structures that would grow into early galaxies. Those early galaxies would merge and evolve, more stars would form. More heavy elements would spread. The simple atomic universe would become a chemically richer universe. But the first stars owed their existence to the simple atoms that came before them, and to the modest chemistry that helped those atoms gather. So the path from atoms to stars is not a side story. It is the next natural movement in the same cosmic process. First, the universe became cool enough for atoms. Then atoms made space transparent. Then neutral gas began to fall into gravitational wells. Then the first molecules allowed some of that gas to cool. Then clouds collapsed into stars. Then stars began making the elements that the early universe could not make on its own. The atom, which began as a simple proton holding an electron, became part of a vast cycle of structure and transformation. And from there, the story begins to turn toward us, though not too quickly. Many generations of stars still had to live and die. Galaxies had to assemble. Heavy elements had to spread through space. New stars with disks of gas and dust had to form. Planets had to gather from that dust. Chemistry had to become richer, wetter, more stable, and more intricate. But the foundations were already present in those first simple atoms and the first clouds they made possible. Hydrogen had become fuel. Helium had become part of the first cosmic mixture. Molecular hydrogen had opened a narrow cooling pathway. Gravity had begun collecting what the universe had made. The first stars were the next great transformation, and through them the simple matter of the beginning would start becoming the varied matter of worlds. And so the simple matter of the beginning did not remain simple forever. Hydrogen gathered, stars formed, stars lived, burned, changed, and died. Their light crossed space, their cores built heavier elements, and their endings scattered new atoms into the dark. After enough time, the universe was no longer only hydrogen and helium, with a few faint traces of other light elements. It became a place where carbon could exist, where oxygen could exist, where iron, calcium, silicon, sulfur, nitrogen, and phosphorus could drift through space and later become parts of planets, oceans, rocks, atmospheres, and living cells. The first atom was hydrogen, quiet and modest, but the story that began with hydrogen did not stay modest. It became stars, it became galaxies, it became worlds, and eventually in one small corner of one ordinary galaxy it became you. That may sound grand, but it is also very literal. Your body is made of atoms, and those atoms have different histories. The hydrogen in you is among the oldest ordinary matter in the universe. Many of the protons inside the hydrogen atoms in your body were formed when the universe was extremely young, long before there were stars, long before planets, long before there was anything like a sky. Those protons survived through the long cooling of the universe, through the birth of atoms, through the formation of gas clouds, stars, and later planetary systems. Some of them are now inside the water in your cells, inside the chemistry that keeps you alive, inside the quiet rhythm of your breath as you listen. It is strange to think that something so ancient can be part of something so personal. But there it is. You carry early cosmic history not as a memory, but as matter. Other atoms in you are younger, though still old by any human measure. The carbon in your body was made inside stars. The oxygen you breathe and the oxygen in water were made in stars as well. The calcium in your bones, the iron in your blood, the phosphorus in your cells, all of these came from generations of stellar activity. Some were forged in the lives of massive stars. Some were scattered by stellar explosions. Some came from processes involving aging stars, collapsing stars, or violent mergers. The details differ from element to element, but the broad point is clear. The heavier atoms in you were not present at the beginning. The early universe did not know how to make them in large amounts. It had to build stars first, and then stars had to build them. This means your body is a mixture of very old cosmic leftovers and later stellar craftsmanship. The hydrogen is deeply ancient. The carbon and oxygen were cooked later in stars. The iron may have been made in a massive star or in one of the explosive events that enrich galaxies. The atoms in your body were not all made in one place or at one time. They are travellers from different parts of cosmic history, gathered temporarily into a living arrangement that thinks, listens, forgets where it put its keys, and occasionally wonders how anything exists at all. You are not separate from the story of the first atom. You are one of its later consequences. It is worth saying this carefully because there is a popular phrase that we are made of star stuff, and it is true in an important way, but it is not the whole story. We are also made of Big Bang stuff, if we may use the phrase gently. The hydrogen in us traces back to the earliest formation of protons and the later formation of atoms. The heavier elements trace back to stars and stellar deaths. So we are not only children of stars, we are also descendants of the first cooling, the first matter imbalance, the first nuclei, the first hydrogen atoms, and the first clouds that gravity gathered. The atom in you is not a simple souvenir from one cosmic event. It is a record of many events layered together, and yet atoms themselves are not alive. A carbon atom in your body is not aware that it is in a cell. A hydrogen atom in a drop of water does not know whether it is in an ocean, a cloud, a cup of tea, or a person trying very hard not to fall asleep during a science video. Atoms obey physical rules. They bond, separate, absorb, release, collide, and rearrange. Life emerges not because atoms individually decide to become alive, but because certain collections of atoms form complex, stable, self-maintaining systems. Biology is chemistry arranged in remarkable ways, and chemistry is the behaviour of atoms and electrons. The path from the first hydrogen atom to a living cell is long, indirect, and full of stages, but without the first atoms, no later chemistry could begin. This is what makes the first atom so important. It was not complex, it was not alive, it did not shine, it did not think. It was just a proton and an electron bound together, but it was the first step into the kind of matter that can form stable structures beyond nuclear particles. Once atoms existed, gas could cool in new ways. Once gas cooled, stars could form. Once stars formed, heavier elements could be made. Once heavier elements existed, planets could form. Once planets existed, complex chemistry could unfold on their surfaces, in their oceans, in their atmospheres, and in warm little environments where molecules could begin doing interesting things. The first atom did not contain all of that as a tiny hidden plan. It simply made the next steps possible. There is a difference between a cause and a possibility. The first hydrogen atom did not cause you in a direct simple line, like one domino knocking over the next with no uncertainty. The universe is not that tidy, and frankly, most kitchens are not that tidy either. But the first atom opened a physical possibility space. It allowed matter to become neutral, light to travel freely, gas to gather, stars to form, and chemistry to begin its long expansion. Without atoms, there is no chemistry. Without chemistry, there is no biology. Without biology, there is no one listening to a story about atoms late at night. So the first atom is not your parent in any ordinary sense, but it is part of your ancestry in the language of matter. When you look around the room, every object is also part of this story. A wooden table contains carbon, oxygen, hydrogen, and other elements arranged by a living tree. A glass of water contains hydrogen from the early universe and oxygen from stars. A metal lamp contains atoms forged by stellar processes and later gathered into Earth. A blanket is made of fibres built from molecules, and those molecules are built from atoms, and those atoms were gathered from the same cosmic inventory. Even something as ordinary as dust is a small archive of atomic history. Dust may be inconvenient on a shelf, but on cosmic scales, dust is essential. It helps form planets, molecules, and new stars. It is also a reminder that the universe has a strong interest in scattering tiny particles into places where someone will eventually need to wipe them away. The echo of the beginning is not only inside matter, it is also in the light that still fills the universe. When the first atoms formed and the cosmic fog cleared, photons were released to travel freely. That ancient light has been stretched by the expansion of space into a cold microwave glow. It comes from every direction in the sky. We cannot see it with our eyes, but instruments can detect it. It is one of the most important pieces of evidence for the hot early universe. In that faint radiation, scientists find tiny variations that reveal the seeds of later structure. The same event that allowed hydrogen atoms to form also allowed the oldest observable light to begin its journey. So the first atom left two kinds of legacy. It made matter familiar, and it freed the earliest light we can still study. There is something comforting about this. The universe did not erase its childhood completely. It changed, expanded, cooled, formed stars, formed galaxies, formed planets, and became unimaginably complex, but traces of its early state remain. The hydrogen still exists, the helium still exists, the microwave afterglow still exists. The pattern of galaxies still reflects the tiny density variations of the young universe. We live in a late and complicated cosmos, but the beginning is not gone. It is folded into the present. It is in the atoms, in the background light, in the large-scale structure of space, and in the fact that matter behaves as it does. Of course, the phrase from nothing remains difficult. Science can tell us how the universe changed from an early hot dense state into a universe with atoms. It can tell us how energy produced particles, how matter survived antimatter, how quarks became protons and neutrons, how nuclei formed, how electrons finally joined nuclei, and how hydrogen became the first abundant atom. But the deeper question of why there is something at all is still open. Physics can reach very far back, but not all the way into a final answer that satisfies every version of the word nothing. Maybe the word nothing is too simple for the edge of reality. Maybe there was never a kind of nothing that our minds can picture. Maybe space, time, and physical law began together in a way that does not fit ordinary before and after. These are not failures of imagination. They are signs that the universe is deeper than our everyday language. Still, what we do know is extraordinary. The first atom did not appear fully formed in a quiet void. It emerged after the universe expanded and cooled enough for matter to become stable. Before atoms, there were particles and radiation. Before nuclei, there were protons and neutrons forming from quarks. Before stable matter, there was a near balance of matter and antimatter, with matter winning by a tiny margin. Before chemistry, there was plasma. Before stars, there was neutral gas. At each stage, the universe became capable of something new. It did not jump from nothing to everything. It unfolded through conditions, thresholds, and transformations, and the atom in you is a piece of that unfolding. Right now, as you breathe, hydrogen and oxygen atoms move through your body in water molecules. Carbon atoms form the backbone of organic molecules. Iron atoms help carry oxygen in your blood. Sodium and potassium ions help nerve signals move. Calcium helps muscles work and bones hold shape. Phosphorus is part of the molecules that store and transfer energy in cells. These atoms are not decorative. They are active participants in your life. They are ancient matter arranged into present function. For a brief span, the universe has gathered them into you. Brief is not meant sadly. It is simply true. Atoms pass through forms. The atoms in you were once elsewhere and will one day be elsewhere again. Some may have been in ancient oceans, rocks, plants, air, or other living things. Some may become part of soil, water, atmosphere, or future organisms. Matter circulates. The atom is stable compared with a body, but its arrangements change. You are a temporary pattern made from long-lasting ingredients. That might sound unsettling at first, but it can also be peaceful. Nothing about you is cut off from the rest of the universe. You are not an isolated object placed into existence. You are a process made of cosmic material shaped by Earth, biology, time, and experience. This also gives ordinary moments a quiet depth. Drinking water is not only drinking water, it is taking in hydrogen, whose history reaches back to the early universe, and oxygen forged in stars. Breathing is not only breathing, it is exchanging atoms with the atmosphere, with trees, with oceans, with the long chemistry of the planet. Resting your hand on a blanket is not only touching fabric. It is atoms in your skin interacting with atoms in the material, electromagnetic forces preventing them from passing through each other, the everyday firmness of the world created by invisible interactions. The universe becomes intimate not by becoming small, but by being present in the small things. The first atom was hydrogen, but hydrogen alone could not make a world like ours. It needed stars to build heavier atoms. It needed stellar explosions to scatter them. It needed gravity to gather them into later clouds. It needed planets to form from enriched material. It needed Earth to develop oceans, crust, atmosphere, and chemistry. It needed life to arise, adapt, and eventually become conscious enough to ask where atoms came from. The path is long and full of uncertainty, but it is continuous. No stage floats free from the earlier stages. The atom in you is connected to the first atom not by metaphor alone, but by physics. As we come back to the quiet room around you, perhaps the objects nearby feel slightly different. Not magical exactly, but older. The wall, the pillow, the glass, the air, your own hands, all made of atoms with histories that began far beyond Earth. The universe is not somewhere else. It is not only in telescopes, nebulae, or distant galaxies. It is in the ordinary matter of the present moment. The first atom was not a separate ancient curiosity locked away in the past. It was the beginning of a material tradition that continues in everything around you. So let me ask again gently, wherever you are listening from tonight, what small piece of the universe is closest to you right now? Maybe it is your hand resting on the blanket. Maybe it is a glass of water on a table. Maybe it is the air moving softly as you breathe. Maybe it is the pillow under your head, patiently doing more for your evening than it ever gets credit for. Whatever it is made of atoms. And those atoms are not new arrivals, they are old travellers, shaped by the beginning, by stars, by planets, and by the patient sorting of time. If this journey through the first atom has brought you a little calm, or given your thoughts somewhere quiet to wander, I would be ever so grateful if you gave the video a like, subscribed, and shared this little corner of physics with William, with someone who might enjoy a slower walk through the universe. It helps these gentle science stories find other curious minds, especially those who like their cosmology, with a soft landing and perhaps a cup of tea nearby. We began with a question that sounded almost impossible. How could the first atom come from nothing? Along the way, the answer became less like a single moment and more like a long sequence of becoming. Nothing in physics is not an easy word. The first atom did not simply pop into a finished world. It emerged from a universe that expanded, cooled, formed particles, preserved a little matter, built nuclei, waited through a glowing fog, and finally allowed electrons to settle. Hydrogen appeared, light travelled, gas gathered, stars formed, and heavier atoms followed. And now, after all that, here you are, made of those atoms, listening inside a universe still carrying the echo of its beginning. So rest now, if rest is near. Let the thought be simple. The atoms in you are old, but this moment is new. The universe has taken a very long road to arrive at this quiet breath, this small room, this listening mind, hydrogen from the beginning, carbon from stars, oxygen from stellar fire, all arranged for a little while into you. Sleep well, fellow traveller, made of ancient matter, held in the present, and gently connected to the first atom that ever learned how to stay together.